Hello.
Good evening.
Yeah. So, yeah. Okay. You can unmute yourself, right? All of you.
Yeah.
Yeah. Okay. Fine. Okay. Can you see me my screen?
Yes, sir. Yes.
Okay. Great. Okay. So, I think this Friday is your deadline for this week 3 contents. So, how many of you have seen all the lectures of week 3?
I've seen all the lectures and having lots of doubts.
Lots of doubts. That
So the deadline is shifted from tomorrow to Friday.
Yeah. Have not you got any mail for that?
No, sir, still not got any information.
Oh. But if you
Yeah.
see in your portal, what it
Yeah.
is showing?
Yeah, graded assignment page, it is there.
It is there, no? Deadline
Yes,
is
sir. Yes,
shifted.
sir.
Yeah.
Yes, sir.
Yeah. So deadline is basically Friday. Friday is your deadline, and we are having one more live session on week 3 on Thursday. Thursday evening, 6 to 8.
Yes, sir, because there has not been any live sessions for week
Yeah.
3
Right.
practice assignments and all.
Right. So today is the first live session for week 3, and the second one will be on Thursday.
Sir, I was waiting eagerly for a live session.
Yeah. Okay. Great.
Sir, can you just show the 3D image of vectors if possible? How to draw them?
3D image of vector. So, have you seen the tutorials?
No, I
Um,
haven't, but I mean, just drawing them simply graphically, not just once
okay,
afterwards.
okay. So, I will do that. Okay.
Sir, would we be discussing the practice assignment today, sir? It would clear a lot of doubts of everybody.
So basically, what I am planning to do is I will discuss the concept a little bit for each.
Yes, sir.
I mean, whatever the concepts are there in week 3, and I will
Okay.
try to solve some problems related to that. Okay.
Sir, actually, I have problem in first lecture, very first lecture. So the practice assignment question number 1 will solve a lot of doubts.
So basically, if I discuss this concept, then I think you can do that.
Yes, sir. Yes, sir.
So
Yes,
Okay,
sir.
let us start.
let's try that. Yeah. Okay. So this is the first thing which I wanted to say, and another thing is I was thinking to share this one also.
So basically, I have one doubt regarding what a vector space actually is.
So can any of one you just start with saying what a vector space is? I mean, what have you understand about that? Any one of you?
It's basically arrangement of numbers into rows and columns.
That is matrix. No? Arrangement of number of columns in rows and columns are basically matrix. But what a vector space is?
The vector which satisfies all the 8 axioms is called vector space, is what I felt.
But I mean, why suddenly these axioms are coming?
Sir, basically it is a set, which is
First of all, it is a set, correct? And then
it is defined over this R. This is what is actually known as field, but some rules are there for the elements of this set, and this is what governs this 8 axioms. Like this 8 axioms come from the rules for the members of this set.
okay, yeah, correct. But why suddenly
This
we need
this
this
is
rule?
only the theoretical.
I am coming to that. I am coming to that. Yeah. So why suddenly these rules are discussed? Why suddenly we have taken these axioms?
Sir, I think it's a space consisting of vectors
with the associated and commutative operation of addition of vectors and associative and distributive operation of multiplication by vector by scalars.
Correct. So, I mean, what is the 0th example comes to your mind? I mean, what is the basic example which comes to your mind when we are talking about these vector spaces? I mean, what is the first example comes to your mind?
The XY plane.
Before that also,
Quadratic
is not any
equation.
example?
Set relations and functions.
No, that is a little bit.
Quadratic equation.
So coordinate geometry.
It has
Much before that, when you study
Linear equations.
just if you think just real numbers, set of real numbers.
Set of real numbers.
Okay. So suppose I don't know real number. I only know what an integer set is. Set of integers. Okay. Or forget it, not set of integers. Set of natural numbers. Let's begin with there. Set of natural numbers. So if we add two natural number, what we'll get? We'll get a natural number, right?
Yes.
Yes.
Yeah.
Yes.
Is this same thing happen if you multiply a natural number with another natural number?
Similar.
Yes, sir.
Same thing.
Yes, sir.
Yes, sir.
And
Yes,
the
sir.
natural number.
Okay.
It holds equally.
But if we multiply a natural number with a real number, what happens?
Yeah,
Should it always be inside natural number?
no,
No.
it
No,
will,
no.
No,
it's not
right?
necessary.
It's not necessary. And I mean, what is opposite of addition? That is subtraction, right?
Subtraction.
Now, if we subtract one natural number from another, is it necessary that it will be again inside a natural number?
No,
No.
sir. No, sir.
No, sir. No, sir.
Negative
No.
number, sir. Yeah.
No.
So here the closure property first come in the picture. Okay. So whatever operation we do among the set, it has to be inside the set again. That is called the closure property. Okay. So if we take set of real numbers, we do whatever operation we like there. I mean, addition, subtraction, multiplication, whatever operation you do there, it will always be inside real number. Correct?
Yes.
True, sir.
Yeah. Right. So this is the basic idea. We have to generalize this idea over any set. I mean, whatever set we can do basically. So the first example of vector space is basically set of real numbers, and our operation will be inside this set of real numbers. Okay. So here there are two operations. First is basically addition, and the second one is scalar multiplication. So scalar multiplication means here scalars means all the numbers which are coming from real number, set of real number. That is our scalar set. Right? Till this it is clear?
Yes, sir.
Okay.
Yes, sir.
So this is why we need this axiom. And if you check all the 8 axioms, this is quite natural in the set of real numbers. Right? Whenever I am adding two real number, it does not matter which order I add. In which order I am adding those two. Right? That is called commutativity.
Commutativity. Yeah. Yes, sir.
So let me go to this slide, as I have already started discussing. So now instead of V, at first visualize this as your R. This is set of real number. Visualize this as R. Now think what these operations are. The first one is basically addition of real number. The second one is basically multiply a real number with another one. Correct?
Yes, sir.
First one is, so axioms are, first one is commutative. We know in real number it holds. Associativity, this is called associativity. So if we take 3 real numbers, if we add the first two and then add the third one with that, it is same as adding the first one and adding the last two and adding first one after that. So in which order, it doesn't matter. So these two is quite clear, right?
Yes, sir.
Now what is 0 in a vector space or inside real number? So basically whatever real number I choose, if I add it with that specific number, if I get the same one, that is my 0. So inside set of real number, what will be my 0? That is the 0 itself, right?
Yes, sir.
Great. Now, what is inverse with respect to addition? So this is my addition operation, the first one. So what is the inverse with respect to addition? Basically, if I take a real number, what I have to add so that I will get 0. That is my inverse. So if I say 5 by 3, this is a real number, right?
Yes, sir.
What is the additive inverse of it?
Minus 5 by 3.
Minus 5 by 3, because we have to get 0.
0.
Right?
Yes, sir.
Okay. So this is the first 4 axiom.
Sir, can I ask something?
Yeah, go ahead.
About third point. Sir, can you take any example for that exception which is not holding this?
Yeah, I will definitely do that.
Yes, sir, please.
I will do that.
Yes, sir. I am not understanding the concept of this 0 vector.
Because,
how do
sir,
we check
it's
whether
quite
0 is
simple
present
to-
or not?
Yes, sir, because it's quite simple to visualize that if we are adding 0 in any number and it is the same number.
Same
But
number,
how do we check whether 0 is there or not? Then
so
we would add 0.
exactly.
Yes, sir.
I will come to that. Let me
Yes,
finish
sir.
this discussion,
Okay.
then I
Sure,
will
sir.
give you the example. Okay.
Yes, sir. Yes, sir. Thank you, sir. Yeah.
Okay. Now, yeah.
Sir, closed means if I add two vector, again it is a vector, and if I multiply any number with a vector, again it is a vector.
Exactly.
Is that, no?
Exactly.
Sir, could you give some example of an open vector, like which is not a closed
Not open
one?
vector. I am not saying these are closed vector. These two are called Gaussian property. Okay.
I mean, there's something which contradicts this also, right? The non-closure ones. Any?
So that I am saying no. So see,
Those will
if we
be
have
under a
this
domain of complex numbers, right? Which are not.
we don't have to go till complex numbers. Say this is my set. Okay.
Okay.
I have addition here, correct?
Yeah.
And I am doing scalar multiplication. So scalar multiplication is basically R cross N. It should be inside N, right? Always.
Yes, sir. Whichever
Is it
will
always
lie
happening?
outside that, that will be the outside of that space.
Suppose I am taking R to be minus 2 and natural number is suppose I am taking 3. So is this scalar multiplication is closed?
No, sir.
No, right?
Why?
Why, sir?
Why? I mean, what is this multiplication? After multiplication, what I am
Minus 6.
getting?
Minus
It is.
Minus 6 a natural number?
It is not a natural number.
Okay, it is not.
So is it clear? I mean, there can be some set with the operation where it is not closed. Closed
Yes,
under the operation.
Okay.
So
now
this is not closed under operation, not closed under scalar multiplication.
Sir, are we
that they will be defining, no?
We
That,
can conclude that division and subtraction is not closed.
No, see, that depends on the set. So this is the first example coming to my mind, that's why I am giving this.
we
But
have
there can
assumed
be
that
many examples like that.
we have taken set of natural numbers, right, sir?
Yeah, set of natural number and usual addition.
And
I have taken only that example.
however, set could be anything.
Set could be anything.
but they will be defining, no? What?
Yeah, we will define. So, I mean, that is the point. If we can define that addition or scalar multiplication to be closer under this two operation, then it will be a vector space. I mean, if it satisfies all these properties.
But here in your case, R is multiplied with natural number to get natural number. Like that, where they will be defining what exactly we will be getting. What is the?
No, I am taking the usual definition of scalar multiplication, but that is not closed.
Sir, can we consider?
No. My doubt is now for you are telling that it will should give a result of natural number. Okay.
No, if it is closed, it should be inside natural number, but it is not closed. That my point is.
Okay. The definition of the closed is it has to be a natural number.
Yeah, exactly.
Actually,
if this map is defined, then we call it closed under scalar multiplication. But it is not defined there. Right?
Natural number includes 0, right?
I mean,
Closed
in
means-
this course we are taking
Closed
that.
means, yes, sir. Closed means that the result lies in the defined set and none of the
Exactly.
elements is outside
Exactly.
that set.
Exactly.
Sir,
I have a question.
Can you please define the closed concept? I joined little late.
Sir, can I ask one question?
Sir, 1 second.
Yeah, one by one.
Plus colon v into v, no? We need to have V plus V, no, sir, because it's addition. Why do we have V into vector into
No,
vector?
yeah, okay.
That is
So do you
Cartesian product.
remember what this Cartesian product is? What this cross sign mean?
Cartesian
Up to
product.
say, this is Cartesian product, right?
Yeah.
If I am taking A cross B, what does it mean? I am taking A B such that A is inside A and B is inside B, correct?
Yeah.
So when I am defining addition from V cross V to V, what does that mean? It means, so this is V cross V to V. So I am taking two vector V1 from V and V2. This is also from V. I am defining addition like this. Okay.
Yeah.
So this is the operation. I am taking two vectors, taking a pair, and I am defining a relation between them, defining an operation between them. That is the addition operation. That's why it is written like that.
Sir, here in the definition, you have never mentioned that it should give an output of natural numbers. Where it is?
No, natural number. I mean, this is for arbitrary any set. Okay. That was an example where I have taken natural number. Natural number is not a vector space.
Sir, can we consider natural number to be a function?
Huh?
A functions are there. It's a set.
Natural number is a set.
Okay. V cross V is a Cartesian product. It can be defined like a function also.
Yeah, it is a function.
Sir, one more.
It is a function from V cross V to V.
Yes, sir. So similarly, the example we have taken here is natural numbers. So it will be natural numbers cross natural numbers, which is function from natural numbers to natural numbers.
Natural number cross natural number to natural number.
Yes, sir. So, so function is from natural number to natural number.
No, natural number cross natural number to natural number. You are taking two natural number, your function is adding them.
And yielding again natural number.
Yielding again natural number. So your output will be one natural number, but your input is two different natural numbers.
So the input is two natural numbers and output is another natural number. So function is of natural number.
Function is natural number cross natural number to natural number.
Yes.
Okay.
You are taking two input, not one input.
Yes,
right?
sir.
In this case, there is no confusion. It will give
it will be inside natural number, right?
Okay.
So addition is closed under natural. I mean, if we take natural number as our set, the addition is closed. But the second property will not hold. This.
Why, sir? If you take R, okay, because we are taking a.
If you take the product, it may not be a natural number, no?
It is but natural number to natural product of two natural number is always natural.
No, this is fixed. This is R. This must be R.
This
cannot be natural number.
Okay.
Okay.
Okay. This is what.
That is why scalar multiplication. This scalar means from R, from a field. So we are not going to field. We are only taking R, real number.
Okay. For addition, we take only natural numbers.
Sir, in the second case,
we
have
are
to
not
consider
taking it. So I am giving you an example where I am taking my set to be a natural number.
Okay.
This V. This V can be any set. Okay.
Okay.
V can be any set.
V can be any set.
Any set. So for giving you a counter example, I am saying let's take V as a natural number set. That natural number set, if you take addition as an operation, it will be closed. But if you take scalar multiplication, it will not be closed. Is
because of negative numbers as well.
Exactly.
In real numbers.
Exactly.
Sir, and suppose if we have a scalar multiplication and we have n tuples in a set. So suppose 1, 3 and 4 consist of the vector. So then if in scalar multiplication, it's not necessary that we have to multiply.
Let him finish with the addition first. He is explaining the concept. Let him explain, please.
Okay. I will
we have still not do multiplication.
Let me hear our question, then I will come. Yeah.
So we don't have to multiply that scalar with all the elements in that vector, no? It's not necessary, right?
It's not necessary. It depends on the definition. How we are defining this scalar multiplication.
Okay.
Okay. So if we multiply this scalar with all the coordinates, that is one definition of scalar multiplication. That there can be many different definitions.
So even multiplying it with one element is also valid, right?
Valid, but you have to check whether it forms a vector space or not.
Acha.
In that case, it may not form a vector space. I mean, this condition may not be satisfied.
Those all 8 axioms, right?
All 8 axioms should be satisfied.
Acha.
Otherwise, it will not be a vector space.
Sir, but in exam to verify all these 8 axioms, it is a tedious task. So is there any shortcut for that?
I will tell how you will approach that problem.
Okay, okay.
So one more thing.
Sir, I have a question.
Sir, please explain the concept, sir.
Yeah, go ahead.
Sir, you gave one example that -2 into 3. -2 is a real number, but the operation is not closed. But here it is written that R into V is closed.
I mean, it should be closed. It is called a vector space if all these hold. So I am saying that n, I mean set of natural number with respect to usual scalar multiplication is not a vector space because the operation is not closed. Is it clear?
Sir, cannot understand the definition of vector space, the first line. I cannot clearly understand.
It is not clear, sir. Can you be, you kind enough to repeat again?
Yeah. So, listen what I am telling, okay? V, we are starting with a set V, okay? Any set, this V can be any set. This V, we call it a vector space. Any set, not only natural number, any set, okay?
Sorry
it
to
can be
interrupt.
any set. Yeah.
So can you please write 1, 2, 3?
Why?
No, as an example.
I'm asking just an example for my understanding. 1, 2, 3.
Set 1, 2, 3.
Yeah, 1, 2, 3. No, 1, 2, 3. Then next row 4, 5, 6.
That is
1, 2, 3.
You are saying a matrix or something like that?
Matrix. 1, 2, 3.
No, why? Okay, don't go there. Okay, don't go there now.
My question was is that vector space?
First of all, understand what a definition of vector space. Then you can tell yourself.
Sir, before we move ahead, can I ask one question, sir?
Yeah.
Sir, if we are considering a vector space V, that is our friend was saying 1, 2, 3. Are we supposed to consider it 0, 1, 0, 2, 0, 3 vector?
First of all, you tell me what is a vector space. First of all, you tell me what is a vector space.
X, Y, and Z means 1, what he is telling is X, 2, what he is telling is Y, and 3, what?
No, first of all, tell me, have you understand what is a vector space?
Sir, vector space
sir.
can be defined over
So
R1,
let me
R2.
let me tell you that. Then you can ask this question.
Okay.
Yes, sir.
Everybody is
Okay. So I am starting with a set. Okay. V is any set. Okay. Whatever the set it can be. Any set. Now I am saying we call this V is a vector space if we can define two operations. One is addition, another is scalar multiplication. And how we are defining it? Addition is defining V cross V to V. What does it mean? We are taking two elements from the set, any two elements. Suppose A and B are from V. If I add these two elements, it should be inside V. Okay, this is called closure property of addition. Closed under vector addition. It should be. Then scalar multiplication. Scalar multiplication means our scalar will come from this set of real number, and I am taking an element from V, and it should be inside V. What does it mean? Say I am taking any real number C. C is from any real number. I am taking any element from V. If I multiply these two, it should be inside V itself. So this is called closure property of scalar multiplication.
Sir, shall I consider this vector as a straight line, number line, such that it
let me finish this. Then you ask this question, then it will be better, I think. Okay. I finish one time, then you can ask. I will take your question. Okay.
Okay.
Yeah. So what I am saying, I am taking any set. So set means there are some elements, right, inside the set. I am taking any two element, and I am defining an addition there. How I am defining the addition? How addition should be? If I take any two elements. If I add those two elements, the end result should be inside the set itself. That is the first condition. The second condition is if I take any real number and I multiply it with the element of that vector space, it should be inside the vector space. This is the first two property, which is called closure property. Now I have defined, suppose I have checked that for that set and these two definition, addition and scalar multiplication, this closure property hold. Till now we cannot say whether it is a vector space or not. Till now we can only say that the addition and scalar multiplication is defined so that it is closed. Only till that portion we can say, but we cannot conclude that it is a vector space or not. There are furthermore 8 axioms to be checked to conclude that V is a vector space. Now we define the addition. Now addition should be commutative. This is the first property. I mean, in what order we are adding this, that does not matter. This is commutative. Second is associative. This is called associative. That means in which order we are adding. Suppose I have 3 elements from my set. I am adding the first two, then adding the third one. It should be same with adding the second two, I mean last two and the first one. That is called associative. The third one is there should be a 0. 0 means what? 0 means such an element inside the set should exist so that if I add any vector, any other element from the set, it will give me the same element. The fourth one is basically existence of additive inverse. That means if I take any element, what element I should add with that so that I will get back my 0. Right? So that is called additive inverse. So these 4 conditions I have to check first. Then I have to check another 4 conditions depending on the scalar multiplication. What is that? 1, if I scalar multiply 1 with a vector, I should get back the vector itself. I am adding 2 real numbers. This A and B are real number. I am adding 2 real number. I am multiplying with the vector. It should happen like this. I am multiplying the real with the vector separately and add them. I should conclude the same result. The third one is...
So this is distributive property, right, sir?
This is distributive property. The
So
third one
here
is...
A and B are any constants, right? And
A and B are
is
any real number.
okay, and V is the vector.
V is the vector, correct.
Okay.
And the third one is, if I take any real number, I am adding 2 vectors, V1 and V2, and scalar multiply with that. Now, if I do it separately, I mean, I am taking A and scalar multiply with V1, and again similarly with V2, and add those 2 vectors, then I should be inside, I mean, should get the same result. The fourth one is...
So this again is distributive property.
But this with respect to the vector. Previous one with respect to the real number.
Okay. So AV plus BV, should it belong to the same vector space?
I mean, that is already done, no? This all should going inside the V now, because these 2 I have checked first, whether these are closed or not. Once I check this, all this is happening inside V now.
Sir, I understand the properties of vector space, but I really don't understand the definition of vector space. So I do not understand the definition of vector space.
That's what I am telling, no?
Sir, in rule number 3.
Let sir complete first.
Yeah, go ahead. What happened in rule number 3?
Sir, rule number 3, there exists an element 0. That means in the vector element, suppose the vector elements are 1, 2, 3, and there should have another 0.
Okay, I am coming to that. I am coming to that. Okay. So basically, I mean, if you don't understand the definition now itself, but at least you understand, you have to check all these conditions. That is clear, right? How you have to check, I will tell you. But at least you understand that all this, if all these condition is satisfied over a set, then only we call it a vector space, right? Okay.
Yes,
now
understood the conditions, sir. Right.
Now say, suppose I am starting with something. Suppose take V to be R2. Okay, you know R2, XY plane. So how the elements of this set look like? How this set look like?
1, 2, 2, 3. Like
X comma y such that x and y both are from real number, right?
Yes.
This is my set. Okay. Now I have to define addition. How I am defining addition?
Here I have
V cross V to V. Okay. So basically I
here
am taking two vector. My first vector is x1, y1. This is my one vector, right? The second vector is
x2, y2.
x2, y2. I am defining this addition.
Can I ask a question, sir?
Yeah.
See here V equals R2 we are defining.
Yeah.
But this symbol R is also same as real numbers. What is the?
You know what R2 is, right? R cross R.
R cross R. Okay. XY plane. Only two.
Yeah.
R3.
So that is my set.
Sir, I
set
want
of
to ask
all
something
tuple or tuple from R cross R.
Sir, I want to ask something.
Vector,
you have defined this vector V.
One by one.
Sir, you have defined this vector V. It is x, y, and x and y belongs to R. And you are defining this addition operation and multiplication option.
Right. I am defining some addition and multiplication on this set.
Sir, is it arbitrary to define or is it given in the question?
It will be given in the question. I mean, when I will say that check something is a vector space or not, that means you will be given a set and two operation, addition and scalar multiplication. These three will be given.
Okay.
These three will be given. You have to check the conditions.
So here the set is x comma y, where x comma y belongs to R. That is the condition set what you are giving. Correct, no sir?
That is the set. Okay, that is the set.
Okay.
Now I am giving you the definition of addition. I am defining the addition like this.
Okay.
Coordinate wise addition, right?
Okay.
Or
and
we can call
how
it
I
a
am
vector
defining
addition.
Vector addition. And how I am defining this? So this is my real number, say any real number, and this is suppose x1 comma y1. I am defining it as cx1 comma cy1. Okay.
This is not the confusion, sir. Actually, here we are telling for multiplication we are taking the real numbers, but for addition, whatever the x1 plus y.
Because addition is on V. Addition is on V.
Addition is on V.
Okay. And scalar multiplication is first element is coming from a real number and second element is coming from a vector.
Sir, can I ask one question?
Okay.
Sir?
Yeah.
And one more thing, sir. For vectors, why we don't put the arrow direction means?
That I learn later. That is not relevant in this part.
Sir, can I?
Sir, your the scalar multiplication, how have you defined for both variables or one? How to understand that?
That will be given in your question.
Sir, but here you have not defined it, no?
No, I have defined on both variables.
But that's what I told you in one of the examples. There they had multiplied the scalar with only one of the elements from the
then
vector.
you have to check whether the rest of the condition is satisfied or not. That is the point. I am taking, this is my first example, so I am taking this.
So, but how to get that, whether it is will be satisfied or no? That's what I'm not understanding.
So I will check that. I will check that now.
It will be given in the question, madam.
I will
you
check
are
that.
saying the condition is given, you have to check the condition.
I have to check the condition. That is the point.
Okay.
Till this far
That's why
it
the
will be
condition
given.
is given.
Now the question is V a vector space?
Acha, okay,
Clear?
Whether it is multiplied by
It
one
can be
element
given
or-
like this. Suppose I can given like this also. The question will be said. Basically, you have to check all the 8 axioms. That's the point.
Sir, there will not be any R1, na?
Huh?
R1 will not be there. R2, R3 will be there.
Why R is also a vector space, no? The same thing will happen.
So can we-
That I have started with. R is a vector space. Huh?
Can we do one question, sir?
Please proceed.
I am doing this one. Please be patient.
No, let him go step by step. Okay.
Sir, can I ask one
Take
question?
some examples later.
Go ahead.
Sir, we have you just took the example addition example V cross V to V, where you have said that vector space one V you have assumed x1 y1 and another x2, y2. Okay, sir, can we consider this x1, y1 to be a vector from 0, 0 to x1, y1 in the coordinate
Don't
plane?
confuse with that one. Then you will be more confused when you will go ahead.
X1.
Okay, sir. So
Now,
we have to just
you have
consider in Cartesian form.
You have seen vectors in physics, right? As a arrow.
Yes.
Like this.
That is my doubt.
Yes, sir. Yes, sir.
Like this you have seen, right?
Correct.
Now, if you every time want to see it like this, you will be more confused in this course. Because
okay. We should not go with that approach, is it? Okay.
No, this is the same thing, but you don't have to remember it like that. You don't have to treat it like an arrow. You can treat it like a set itself. That is the beauty of this.
Okay, so we don't have to consider make a picture in our mind that it is x1, y1 from 0.
No, just make a picture of a set.
Just as a Cartesian.
As a point on a R2. As a point on R2. This is your x1, y1.
Like what
you don't have to consider this. Although it will be same thing. But you don't. Every time you don't have to consider an arrow. Just consider it as a point.
Okay, that's what my question was.
Just a point in the Cartesian plane.
Exactly.
We are not putting the arrow. That was my doubt. And here, what we are trying to do is like what we studied in Max 1, correct? No? Coordinates.
The same thing. Basically, on R2 now we will move to R3, R4, anything. Basically.
Okay.
This is arbitrary vector space.
Okay.
So let me. So this is a set given, an operation given, addition operation, a scalar multiplication operation is given. These three are given, correct? First of all, tell me whether addition is closed or not. What does it mean? If I take any two elements from R2 and do this addition like this, how I have defined, will it be inside R2?
Yes, sir.
Yes,
sir.
Because
Correct?
x1, x2, y1, y2 also belongs to the...
Exactly. All of them are belonging to R. So whatever I do, it will be inside R2. Correct? So I am saying addition is closed. This is the first thing you have to check. Now, second one. Is the scalar multiplication closed?
Yes.
Why?
Because
Because the resultant elements will also be from R.
Multiplication of real with the real is always the real.
Exactly. This is inside R. This is inside R. So the tuple is inside R2. So scalar multiplication is also closed.
But R is a real number, no? So as if you take minus something, then also it will be.
It will be R, no?
It will be R.
Right?
Can you please
sir,
relate?
this last point I couldn't get it. B, see.
B is also R2. So whatever that be, it will be inside R, no? This C is inside R. This X1 is inside R. So where CX1 will be?
Inside R.
Inside R, right?
So B equals R2 means, can you little bit elaborate?
Hey, you are going round by round now.
No, that's
B is R2 means what? It is a point in R2 plane, XY coordinate.
XY coordinate, yes. That is.
So X is coming from R, Y is also coming from R.
Just recall the concept of tuples.
Right? Now I am multiplying C with the first coordinate. The first coordinate is inside R. The C is inside R. So where the product will be? It will be inside R, right?
Yes.
Can you please relate this question to where addition is not closed and scalar multiplication
First
is
of all,
not
let
closed?
me define one thing at least, which is a vector space. Then I will go to the counter example.
Yes.
Okay.
So CX1 and CY1 will also be in XY plane. That is what you are correct.
Exactly.
Okay.
Right?
Because
so addition and scalar multiplication, both of them are closed, right? Till this point it is clear.
Here? What is the meaning of tuple here? It means a row.
Tuple means A, B, C like that. So here it is R2, so the first coordinate and second coordinate, first is coming from R, second is also coming from R. That is a tuple. This X, Y is a tuple basically. PR.
Actually, the thing, that meaning of tuple is that only if sir has taken a set. Set need not necessarily be 1, 2, 3. Set could be 1, 2, bracket, comma 3 comma 2.
I think that he can understand.
That is tuple. Our friends
This
are
pair. This pair is
pairs can also form a set.
Okay, got it. Thank you.
No. Here, since it is R2, we are only restricting x comma y. If it is R3, means x comma y comma z.
Exactly.
Yes.
And many sets of three elements. There will be many elements.
But x can be only one element, right?
So tuple is basically one element or the entire xy, both?
No, collection.
This is a tuple. Suppose I am writing 1 comma 2. This is a tuple.
Okay.
There cannot be any 1 comma 2 comma 3 like that. It cannot be
it cannot be inside R2. It will be inside R3, but it is also called a tuple. Tuple means a collection. I mean, something like this: A, comma B, comma C, comma D. This is called tuple.
No, sir. My doubt is inside this bracket, another bracket. It cannot be now. What I mean.
Yes. There can be. That is set. That will be a set.
That's my question. For example, you open one bracket, sir. You open one bracket. Just okay. Another bracket.
No, I am not taking that.
Okay.
Only element like 2, 4, 7, 9,
like that.
5.3, 6.2, or like all the elements like this.
Okay. All belongs to real number.
Like that also it can be or cannot.
I mean, all these elements are here.
Okay.
Krishna, is it you? Krishna Ji,
yes,
right?
Yeah.
So, I mean, you have done this Maths 1 course, right?
Yeah, in Maths 1 course, what? No, x comma y means it is x is.
No. I don't want to know that. But in Maths 1 course, have you learned what a Cartesian product is?
Yes.
What is a Cartesian product?
Means what do you call it? It's in the coordinates.
Can you do one thing? Can you just go back to the first week of the shape theory, where shape theory has been introduced? Can you go back to that lecture and just see what Cartesian product is? Then I think it will be clear to you. Okay. You just go back there and you see what a Cartesian product is. There, Madhavan sir has mentioned what R2 is. R2, R3.
Okay.
Just take a look there. I think then it will be more clear.
Set of all ordered pairs, basically.
Okay, right.
More appropriate.
But this is not order. Yeah. Anyway, so it is clear, right? This addition and scalar multiplication is closed. At least this part is clear.
Yes, clear. This is clear till this point.
Now, what is the first axiom? X1, Y1
commutative axiom
plus
of
X2, Y2 should be equal to in opposite order, right?
Yes.
Now, is it that?
Yes.
So this is my addition. Now, what is X1 plus X2? This is same as X2 plus X1, right?
Yes.
And this is same as Y2 plus Y1. And this I can write as X2 comma Y2 plus X1 plus X1.
Or if we ascertain that the vectors are not closed, then we don't have to follow all this. Then it is not at all.
If in the first step you see that addition is not closed, then you don't have to check anything.
Okay.
You can directly say that this is not vector space. Okay. Once you fail, you don't have to check further. Okay.
Yes, sir. Thank you.
Sir, can we discuss the last line you have just read?
This one, right?
X2 comma Y2 plus X1 comma Y1.
So
what does this signify?
All are real and we can shuffle them. Right?
This is real number. All these are real number, right? So I am doing the addition X1 comma Y1. This is my V1. This is my V2. Right? And how addition was defined? Coordinate wise addition, right? X1 plus X2.
Yes, sir.
Y1 plus Y2. Right?
And we are
if
saying
you
that
see an example 1 comma 2 plus 5 comma 7. What is the result?
6 plus 6 comma 9.
9. Now what is 5 comma 7 plus 1 comma 2?
6 comma 9.
Same thing, right?
Yes,
this
sir.
is what I have done here. Is it clear?
Excellent. Yes, sir.
Yes, sir. Yes, sir.
Clear, no?
Yes, sir.
Everyone, is it clear?
Is it necessary, sir, in
Yes,
the third line above X2 Y2 plus X1 Y1? Is it necessary to shuffle the items in these two tuples? We are not adding coordinate wise, right? We are adding x with y coordinate.
What? No, we are adding coordinate wise.
Is it nice?
X2 and Y2 are not the. We are not adding.
I am not adding X2 Y2 anywhere.
X coordinate
Sir, as
X2 comma Y2, this is X1 comma Y1, this is V2 and V1. This is
X coordinate with X coordinate, Y coordinate.
just interchange the second line with.
Just shuffle this. X1 plus X2 is basically X2 plus X1. So here it is 1 plus 5 is same as 5 plus 1. That's my point. Okay?
Yes, sir.
Is it
Yes,
clear,
sir.
everyone?
Yes, sir. Yes, sir.
Yes, sir.
Okay. If something is not clear, you tell me, because this is the first lecture of vector space. If you don't understand it, the whole section till week 9 will go wrong. Okay. So
Yes,
this is the first one. What is second one?
Scalar multiplication. No.
Second one is associativity.
Associativity.
Right. This is commutativity we have got. Second one is associativity. That means suppose I have 3 vector. So let's take 3 elements like this. 7, 3. Okay. So what it means? If I take these two first, what I am getting? These two first.
12, 10.
Then if I add this, what I am getting?
13,
12.
Great. Now if I take the first two to begin with, this one,
6,
then I am adding 7, 3. So what is the first, this one?
6,9.
What is the second one?
7, 3.
Now what it will be?
13, 12.
So can you see that these two are same?
Yes.
Yes, sir.
Right. Same thing. Basically, I now have to write in symbols. I am doing the same thing, just writing in symbols, because this is for any element, right? This is for particular example I have taken, but I have to prove it for any element, right? So what it is? It is, the first one is x2 plus x3 plus, comma,
y2 plus y3.
y2 plus y3, right? Now, if I add it with x1 plus y1, what I will get?
x1 plus
x1
x2
plus
plus
x2 plus x3, y1 plus y2 plus y3, correct?
Yes.
Okay. Now, I will add another page here. Now, what I have to do? Now, I have to do first two to begin with. Okay. So, what is this one? Tell me.
x1 plus x2.
x1 plus x2.
Then
y1 plus y2.
y1 plus y2.
Great. Now I have to add it with the third one. What I will get?
Same x1 plus x2 plus x3.
y1 plus y2 plus y2.
So whatever my value of x1, x2, y1, y2, x3, y3, whatever the value is, these two are always same, right?
Yes.
This end result. That is what I was supposed to do, right? This is my v1, this is v2, this is v3, right? So this is v1, v2, v3. So what I actually proved? I have proved v1 plus v2 plus v3 equal to v1 plus v2 plus v3, correct? This is what I have proved for any v, correct?
Yes,
is it clear to everyone?
Okay.
Yes, sir.
So I have proved the associativity. Great. Great. So the third one is existence of 0. Now the important part we have come. Now any vector, suppose I am taking any vector, it will be of the form x comma y, correct?
Yes.
Take an example, say 2 comma 5. Any vector I can choose 2 comma 5 I have taken. What I should add it with, so that I am getting back 2 comma 5.
Yes.
What the vector should be?
0 comma 0.
0 comma 0.
0 comma
0.
Right? And this is true for any vector. Instead of 2 comma 5, if I take 7 comma 19, and here I am 7 comma 19, this should be 0, 0, right? Whatever the vector be. Correct?
Yes, sir.
So this V plus something vector which is giving me back V, this vector is my 0 vector. Now, is inside R2 there is a 0 vector? Yes, it is. This is the 0 vector. Is it clear?
And this is also an element of this vector.
R2.
R2.
Correct.
Okay.
So 0 vector is inside our R2.
0, 0 has to be inside R2 or inside V?
V and R2 are same in this example.
V is the subset of
checking
R2.
For R2.
Okay,
no.
okay. Rule wise, it has to be under V, na sir.
But here I am checking an example for R2.
We are taking for R2. Okay.
Exactly. Clear?
A question here. I have a question here.
Yeah.
Adding 0 to this vector will always be the same vector. So why are we checking for this?
No, we have to check
We have
0.
to check the existence of 0 vector inside the set, whether there is a 0 vector or not.
So why add? Okay, but that will be more.
Any example where it will not be a 0 vector, then it will be very clear.
Okay, great. Suppose I am taking. Any other question here?
Yeah, what I mean to ask is, oh boy.
One, Ravi, you tell me first.
What I mean to ask is it not sufficient if 0 vector is a part of the set? If we verify that, should we necessarily add it and check it?
No, you don't necessarily have to add it and check it. It should be a part of that. But the problem is, with respect to this addition, I will come to that later also. It depends on the addition what your 0 vector will be. It may not be 0, 0 always. There can be some different type of addition for which 0 vector is not actually 0, 0. It can be different.
Okay.
Cartesian,
hopefully we will not see such example in this course.
A Cartesian product can be defined in many ways.
Sir, you mean to say it can be something else than 0, 0.
Exactly. Depending on the addition.
So that is going to come in this course or not come in this course?
In this course it may not come.
Okay.
Suppose the elements are -7 and -9.
Sir, it's actually very abstract. I mean,
it is abstract.
I mean, like not.
Sir, can you please pardon this point?
Like non-example is a little bit abstract.
Sir,
non-example will be abstract, but let me.
Can I add one thing, sir, to make the scene a bit more clear? What I understand is that Cartesian product can be defined in many ways. That's why
that
0
is
vector
not the point here actually.
is not necessarily be 0 point.
Can you?
Yes, sir.
Excuse me, sir.
One
Can you please pardon this point?
This is very important point.
Sir,
I mean repeat it, please.
I will
Suppose the elements are -7 and 19. Then the 0 vector is 14 and 38.
No, 0 vector will be unique.
You don't.
Whatever the 0 vector is, that should be unique, and here in this case it is 0, 0. Because.
Sir, I have a question.
Sir,
let me finish that. Then you ask the question.
I have clear.
Sir, I have a doubt here. You were saying 0 vector need not be 0.
In this case, it is 0, 0, but there can be some addition operation where it need not be 0.
Yes, sir. That's why I am saying. Let us take another example. Suppose the elements are -7 and -19.
No, once the addition is fixed, it is 0 vector is fixed. Now, if you change any vector, if you take any vector, then 0 vector will not change because 0 vector is with respect to this addition only. It does not depend on the element.
Sir, addition can be defined differently, right, sir?
Yeah, right.
In that case, it will not be 0, 0.
Exactly.
Sir, I have a question, sir. Sir, actually, my point is that the vector 0, 0 is not actually explicitly present, but we should check if any vector element inside V and inside R2 is same, then we conclude that 0 vector is present.
Can you repeat? I have not got your question properly.
Actually, the 0, 0 vector is explicitly present or not inside V.
Yeah, it is.
That is the point. So first of all, what is 0 vector? You have to know. 0 vectors means whatever vector you are adding with that vector, we should get back the same result. First of all, that is your 0 vector. Now you have to check whether that vector is inside your vector space or not.
Sir, in this case, zero vector is the origin, is it?
Exactly. In this case, zero vector is origin. Yeah.
Can you give an example where zero vector is not present?
Sir,
I am giving.
Sir, one thing, sir. I earlier I said, sir, in the case of addition of for zero vector, earlier I used the term Cartesian product function, the definition in which the Cartesian product is defined. That was, I guess, the wrong term I used. It will be more appropriate to say that the way vector addition is defined. Right, sir?
But the addition is actually a function from v cross v to v.
Okay, it can be defined
now,
in any other
how
way.
you are defining the function, that is the point.
Will that be a Cartesian product, sir?
Which one?
We define, for example, we define v cross v, and then we define the vector addition.
Because for defining addition, you need two elements, no?
Yes, sir.
It should be from v cross v. Correct?
Sir, if same element present in
we are defining, or we can say we are assigning a function to vector addition or the Cartesian product.
No, what I am saying is, see, this, when you are defining addition, suppose I am defining 5 plus 9, I want to check that. You need two elements, no? So
yes,
if I write it as a pair, 5, 9, it is inside some Cartesian product, no? This is coming from one set, this is coming from another set, right?
Okay, sir. Okay.
That is what I am telling. This is the product.
So we can also define it like 5, 9. We can define it like 5, 5 plus 9 vector addition. Some constant plus 9. We can define it that way, no, sir. So we are
but you need two elements, no?
Yes,
you
sir.
need a tuple, right?
Yes, sir. We are having a tuple already, and we are defining the vector addition to be, for example, we are given a tuple x comma y, and we are defining our resultant vector to be x comma x plus y. Vector addition.
Whatever can it
so that is the Cartesian product, or we are just defining the addition that way?
It is both a Cartesian product and we are defining the addition in a different way.
No, see, this is a set V which is R2. That means it is a Cartesian product R cross R. Okay?
Okay,
now,
sir.
when I am defining an addition over R2, what I am doing R2 plus R2 to R2. Right? Here the first element is a tuple, second element is also a tuple. I am defining addition in between these two tuple, and I am getting back a tuple. Right?
Okay, sir. Okay.
Got it, no?
Okay. So basically we are defining the addition. It can be defined in any way. Over a tuple.
Right.
Okay, sir. Got it. Okay. And the Cartesian product, of course, it will be a Cartesian product, the resultant.
Again, that depends. I mean, if you are defining on R, that is not a Cartesian product at the result. That is a single element. If this is 5, this is 9. What is it? It is 40. This is not a tuple. Right?
Okay. Yes, sir.
So what is tuple?
Any element of a Cartesian product. Like this, A comma B. This is a tuple. Okay. Yeah. So
that an example where zero vector is not present.
Right. So suppose I am taking this example. Say x comma 1 such that x is inside R. This set. This is a set, right?
Yes, sir.
This is a set, right? Now my addition is the same thing. Coordinate wise addition. Okay?
Yes, sir.
x1 comma 1. Now my elements look like x comma 1. So when I am
x2
defining my addition, I am defining addition x1 plus x2
plus 2 comma 2.
No, 1, because comma 2, if I define, okay, first if I define comma 2, is this addition closed?
No, it is not closed.
Right? So to make it close, I am defining it to be 1. Okay?
Okay, sir.
Okay.
So I did not get like addition of tuple. It will be 2, right? How can you make it define it?
I
like
am
that?
defining it. That is on my hand.
Sir is
How I am
defining it
defining
as
it.
x, comma 1.
Pratik, I guess you were asking the same question previously. How only it is being multiplied by one element. Similarly, sir is defined only to limited to one element of the
So
tuple.
if coordinate wise defining, suppose I am defining it to be 2. Is it closed?
It will not be closed.
It will not be closed, right? So we can directly say it is not a vector space.
Sir, what do you mean by closed?
Why?
It will be closed now because it is belonging to R.
No.
What is the
it is
meaning
not
of closed?
X is belonging to R.
Is this
Second
inside
element
A?
is not 1.
Is this
X,
inside
comma
A?
1. Definition is x, comma 1, which and where x belongs to R.
X1 plus S2 has to belong to R, and 2 is not equal to 1.
Yes.
See this?
I mean, how the elements of A look like? Something comma 1, but it is 2, so it is not inside A, right?
See, here you are fixing the y. Y you are fixing as 1, and x can be anything. So it is
not anything, real number.
This is a set I
To
am
belong to
choosing.
R.
So it will be like more like a circle with the center at to 1. Correct? Y axis is fixed. Y axis is fixed. So here we are getting 2 as y. So that's why it's not belonging to A.
Right. So that is not closed, right? So this is not a vector space, correct? With respect to this addition.
But this
Yes, sir.
definition you are defining, no, sir? This is what x comma 1. This one you are defining.
If I am defining my addition like this is not a vector space. Is it clear?
Yes, sir.
If my addition is this is not a vector space. Is it clear?
Yes.
Why?
Because we should get 1.
Because this addition is not closed.
Yeah,
Right?
it is not closed.
Till this portion is clear to everyone?
Yes, sir.
Yes.
Any doubt till this
Yes,
portion?
sir.
Very good question, sir. Very good example.
Okay. Now I am changing this definition. I am defining it at 1. Okay.
Then it is correct.
Then it will
Then
be
it is closed, but we don't know whether it is vector space or not. Okay. We have to check the axioms.
Can I ask the
At least
question?
addition is closed. That one we know. Right?
Sir, can we just repeat this line, sir? We have to check what? It is a vector
Axioms.
space. It is closed, and we have to check whether it is a vector space or not.
Right. Now, if I
What is
define the
the
addition
meaning
like
of
this,
closed?
we know.
Exam Papa.
What is the meaning of closed? I mean, how we define closed?
If I add 2 vectors, 2 elements from this set, it should be inside the set. That is the definition of closeness. Okay.
close means
Okay.
It should be
satisfied.
resultant vector should be inside that.
Yes.
Okay. Resultant element should be inside the set.
Yes, that is
Okay.
Thank you.
But can I ask this question? Why 1 plus 1 is again leading to 1? Is there a special understanding that should be made from the definition of the set?
No, nothing special understanding. I am defining this.
It is given.
It is given to you.
We are
I
not
am
doing.
defining
He
We
is
are,
not adding. Actually,
we are
1
not
plus
doing
1.
1 plus 1.
I am not doing 1 plus 1. I am defining a new addition.
See, he is putting only x1 plus x2, comma 1. So 1 is fixed.
Okay.
1 is fixed. We are not changing anything in that second coordinate.
Sir can also write it as x1 comma 1 plus x2 comma 1 is equal to 1 comma 1.
Only 2 elements.
10. You can say 10, but then it is not closed. That is also possible.
We can sir can also make x1 plus x2 as the constant.
No. X1 is variable. X1, X2.
One minute. What?
Is it possible, sir, that you make the first element of the ordered pair also be constant? Both of them can also be constant, na, sir?
Like this, something suppose
10
4.
comma 1. Yes, sir. Is it possible?
This is also an addition, but this doesn't make any sense, right? It will not satisfy any of the property.
It will not satisfy, but we can
Sorry,
define
which
it.
is the addition? You are defining it. That's on your hand.
We have whatever addition we do, result will be 4 comma 1.
Exactly.
But you can put only x1 there, na? If you want to.
Yeah, anything.
Here he can put x1 plus 2x2 or x1 plus 5x2 or something like that. Also
Whatever you think. Just
anything.
you can take anything. That is on your hand. That
And
will
then-
be given in the question. Now you have to check whether
it is closed or
a
not.
vector space or not.
First closed or not, and then vector
First
space.
closed or not, then other axioms.
Vector.
Okay, is it clear?
Okay, sir. Yes, sir.
Everyone, is it clear?
Yes.
Okay, great. So I am taking my set to be x comma 1. I am defining my addition like this. I am defining my scalar multiplication like this. Okay.
Okay, sir.
Okay, now I will check whether the properties are satisfying. So first of all, is it commutative? Is the addition is commutative? Everyone has to participate,
yes.
okay?
Yes.
Why it is commutative?
Because x1 comma x1 plus x2 is equal to x2 plus x1, and one will remain 1.
Now if I interchange this, what I will get? The same thing, right?
Yeah.
So x2 plus x1,
Comma
1. Now x1 plus x2 and x2 plus x1 are same. So these two are same. Correct? So it is commutative.
Commutative.
Fine?
Yes, sir.
No doubt till this?
No, sir.
I am erasing this because it is just...
So just one question. Yes.
Yeah.
On the left hand side, can you say that x1 and x1 comma 2 will also be in the vector space?
No, it will not be in the vector space because vector type set I have taken is something comma 1. So second coordinate is always fixed. If it is 2, then it is not inside the set, right? See, 5 comma 2, is it inside A?
No.
No, right?
5 comma 1 is inside A.
5 comma 1 inside. Right.
So A is the vector space.
I have a question. Like
A is the set. I am checking whether it is a vector space or not. A is the set I have said. And with these two operations, addition and scalar multiplication, I am checking whether it is vector space or not.
You are defining that any addition of y element will always be 1. So how does it matter if it's 2, 3 or 5?
No,
if it is 2,
x belongs to
you are
1.
saying here if it is 2, what will change, right?
No, I'm saying that there you are defining that addition of y element will always be 1. Correct? So why does it matter if y is 2, 3 or 5?
Where?
It will also be in the addition.
Which portion? Here?
Yes.
No. Then is it inside A? Is this element inside A?
No.
No, when we were doing...
No, I want answer from him. Is this element inside A?
That is not my question. There it is 1 only. I'm talking about the left hand side.
Okay, left hand side where?
x1 comma 2 and x2
but
comma
x1 comma 2 is not inside A. So why I will define that? I will define the addition with these elements, right?
Okay.
Right. Addition is defined on V cross V to V. Right. I have to take element from V. I have to take two elements from V. In this case, it is A. And I am checking whether now, after defining this, I am checking whether it is vector space or not. Is it clear?
Got it. Yes.
Sir, when we are doing the associative property, you wrote x.
No, I have checked only commutative. I have not checked associativity.
Sorry, sir. Commutative. So you wrote that. What example you wrote, sir? Can you please write again?
x1 comma 1 plus x2 comma 1. What is this?
So this is x1 plus x2 plus 2 comma 2.
No, 1.
That's how we add coordinate wise. So why is that?
No, that's what we have.
Yeah.
Clear? No, that's how we have defined it.
Yes. It should be this. It should be this.
It should be this. It must be this.
We are not checking here, but we are not checking here, but we'll check that it should be this.
This is the addition. This is the addition for which we are checking.
So, but
here, if I say in this example, see, 1 minute. I am giving you concrete example. 5 comma 1. Is it inside A?
5 comma yes, sir.
Yes, sir.
9 comma 1. Is it inside A?
Yes, sir.
Yes.
What is the addition with respect to the addition I have defined?
14 comma 1.
14 comma 1. Not 2. Because that's how we have defined.
Yeah, defined.
Okay. Now what is 9 comma 1 plus 5 comma 1?
14 comma
14.
So it is commutative, right?
Okay.
Clear? That's what I have written. Clear?
Sir, one small doubt, like in the first line when you were mentioning x comma 1, so in the initial definition if we mention there x comma 2 wherein x belongs to real numbers, so even any number whether it will be 1 or 2, anything can be fixed. It is not necessary that only 1 would be there, right?
Exactly. 1, there is nothing special.
So it depends on the definition what you are putting there in the first line, and accordingly we will move ahead, right?
Exactly. It depends on these three definitions.
Yeah.
All these three definitions.
Okay.
Okay. What is the set? What is the operation? what is the scalar multiplication. Okay.
Sir, one general
Suppose someone give you a set, just a set. They did not mention what the addition is. You cannot tell whether that set is vector space or not until you know what is the addition there, what is the scalar multiplication there. Is it clear?
Yes, sir.
Yeah. Okay.
Yes, sir.
Yeah.
Zero vector.
Yes, sir.
I am coming to zero vector one by one. I am coming to zero vector. Okay. Yeah. Let's be patient. Okay.
Sir, one general question. So how many times in a week we have these live sessions?
Why that question is in between these vector space?
Sorry, because I couldn't get the answer of this question. I sent an email to support.
There are 3 lectures.
You will not deviate.
There are 3 lectures.
Course you will find this solution.
Actually, we were having test this week, na?
Okay.
That's why.
So associativity. Okay.
Yes, sir.
I am adding first to this, then third one, right? What is the answer? What is this two?
1 plus x2,
Plus 1.
Right?
Yeah, x1
If
plus
I add these two,
plus
what I will
x3,
get?
1.
Correct? Now, what I have to do? For second two, I have to do first, right? This two. So what is x1, 1 plus this is x2 plus x3, 1. Correct? Is it clear?
Yes, sir.
Okay. Good. So now again, what I have to do here? X1 plus x2 plus x3, 1. So these two are same, right?
Yes.
Yes.
So this is associative. Clear?
Yes, sir.
Clear till this point? Now
Yes,
what
sir.
about 0?
Yes.
That is the main question, right? So I am erasing this because commutativity and associativity is quite clear. Can you tell me, someone, what is 0 here?
0 here means 0, comma 0, but it's
0, 0. Is 0, 0 inside the set?
no, sir. No. Because
minus x comma 1.
Minus x, no. Minus x means 0.
0, 1.
0,
0,
0,
1, 0, 1.
It's not inside this vector space.
Right. So basically, I have to check any element x, 1. There should be something, something. And that should be x, 1 itself. Right?
Yes, it will
And using this addition, right? Whatever I have defined. So if I take 0, 1 as my 0, is this satisfying this property?
Yes, sir.
Right?
Yes, sir.
Satisfying, right?
Yes, sir. Yes, sir. Yes, sir.
And is this inside A?
Yes, it is also inside it, sir.
Yes,
This is
sir.
also inside A, right?
Yes, it is
0
also
is real
inside.
number. Yes, sir.
So it is inside A. So this is my 0 vector in this case.
Oh.
So this is not 0, 0 always. That depends on the addition.
Okay.
Right? And the set.
The way addition is
depending on the
Exactly. Is it
condition.
clear?
Yes.
So the
Now is it clear that 0 is
Yes,
not
sir,
always
yes.
0, 0?
This is really a great example. Now I got it.
Got it, no?
Thank you.
Yeah.
Yes, sir. Thank you.
Okay.
So,
now tell me what is inverse. Now I think it will be more clear. What is
Sir, I
inverse
have
of-
a question. Sir, I have a question.
Ah.
When we were
Minus x,
defining
1.
vector space and we talked about two operations, addition and scalar multiplication, then we defined that x1, y1 to be one vector and x2, y2 to be the second vector. We defined very clearly that addition would be x1 plus x2 and
That
comma
is
y1
one
plus
example.
y2.
That is usual addition. That is one example. There can be other examples also.
So even this would be satisfying the definition of vector space.
Yeah, see, you are going to see that it will be a vector space eventually.
Okay, so we even consider this type of addition as part of the operation, satisfying the operation addition.
If it is given in your question, if it is given in your problem which you are tackling with, then yeah, it could be. Suppose you are dealing with some data which, which demands this type of addition, then it will be, no? You have to deal with this. You will not always get something.
Adding
which
only
is
one part of the coordinate and keeping the other
Exactly.
constant.
Yeah, some type of data you can get, right? Where one column is basically fixed. One set is not changing for anyone. So what we will do? We will just deal with the first one. That is one example. That will be vector space. Then you have to deal all your machine learning stuff on this vector space.
And suppose if we take 0, 0 in place of the 0 vector, then this entire addition becomes invalid, right?
Entire addition becomes invalid, and 0, 0 is not inside A.
So it won't.
So we cannot take that.
So first we have defined A. It has to be a real number and 1.
So 0 vector, whatever the 0 vector be, it should be inside A, right? We have to take some vector from A. Correct?
So sir, can we say that sir, zero vector is unique vector?
0 vector is unique. Yeah.
Yes. It's
in nature, I think Sarah has already proved it. 0 vector is unique.
Okay.
You need not. You don't need the proof for the course, but okay, you can see. That's not difficult. 4-line proof it is. Okay. Okay. So tell me, what is the inverse?
Minus x comma 1.
Minus x comma 1.
Minus x comma 1. Okay. So this is your inverse. So if you add these two, you will get 0, 1. You should get back the 0 vector, right? This is your 0 vector, remember? So this is your additive inverse. And is this inside A?
Yes, sir.
This is inside A.
Yes.
So all the first 4 axioms are satisfied.
Yes, sir.
Okay.
Now we have to check scalar.
Now you have to check the
scalar
multiplication.
4 axioms for scalar multiplication.
Right.
Sir, just one thing.
Yeah.
Sir,
Last.
One by one. I will give your answer.
So, if we have defined A equals x comma 1, where A belongs to natural number, then the last one won't be valid, no? Minus x comma 1.
Exactly, last one will be valid. Right.
Okay. We have to see the first question based on that one to calculate.
Exactly.
Okay.
Then if x is some natural number, then this is not closed. Because C is real number, no? This is not closed. Okay?
Excuse me, sir.
Yeah.
Sir, just a clarification. So if this addition condition is not satisfied for what we have defined for A, then we don't have to move for other
Forward.
checks,
Exactly.
right?
Exactly.
So
this order is really important.
Okay. And so that means the vector does not belong to the vector space?
It does not form a vector space. So it is not even a vector space. There is no vector space. That is only a set. So we don't know. Don't call those elements as vector. Even in that case.
Basically here x comma 1 is a straight line. If we imagine on the graph, then vector space is all the points on that straight line, right?
Exactly. Y equal to 1. This is basically y equal to 1 line. On xy plane, this is y equal to 1 line. Correct?
Sir, please.
X equal to 1. This is, if you want to see it graphically, this is this set. This is y equal to 1.
Horizontal line.
Right? This is the vector space I am talking about. But this is vector space only when I am taking this as my addition. Correct?
Basically, movement along y is equal to 1.
Exactly. Now, whatever the rest 4 axiom, let's check quickly. 1 into v. Is it same? X comma 1?
Yes, sir.
It is x comma 1, right? Okay. Next axiom was a plus b. 2 real numbers, say c plus d into x comma 1. What is this?
C plus d into x.
C plus d into x.
Into c plus d.
No.
Yes, sir. Comma 1.
So it is cx plus dx, comma 1. Now what is this? This is same as cx, comma 1 plus dx, comma 1. Correct? So this is cx, comma 1 plus dx, comma 1. Okay?
Yes, sir.
So can you check the rest too? It will be same.
Yes, sir.
Okay? So this is a vector space with respect to this addition and scalar multiplication, right? Till this,
sir.
Anyone have any doubt?
Yes, sir, in last line, sir.
This one? This line?
Sir, how I got it till cx plus dx, comma 1.
Now, okay. Now, if you want to check, left hand side, right hand side, that is also okay. But can I write this as Cx, 1 plus Dx, 1? Because if you add these two vector, what you will get? Cx plus Dx, 1, right? So these two are same. Correct?
Okay. Yes, sir.
Now I can take C outside. Basically, I am checking this thing. So C into x, 1, what is that? Cx, 1. D into x, 1 means Dx plus 1. That's what I have written. Okay?
Yes.
Got it, no?
Yes, sir.
Yes, sir.
Yes, sir, got it.
Okay. So this is a vector space with respect to this addition and scalar multiplication. Now, in the same set, I am not changing the set. Okay? I am not changing the set. Now, if I am saying this set with respect to usual addition and vector multiplication, scalar multiplication, is it a vector space?
No,
I
sir.
have already answered it.
No,
but
sir.
Still. No. Why?
No. Because it will become 2 on addition, the second element. And we multiply constant, then it will not yield 1 as the second element, but rather the constant.
Exactly. Is it clear?
Yes,
No,
sir.
what was the question?
Sir, can you explain it once again?
So basically, this set with respect to this addition and scalar multiplication is vector space. That we have proved. So this is an example of vector space. Right? Now I am saying, if I am ignoring this addition and scalar multiplication and I am saying that my addition and scalar multiplication is the usual one. Usual one means coordinate wise addition and coordinate wise scalar multiplication. Then is it a vector space?
No, sir.
No. Then it would
No,
not be.
so the y element will not satisfy.
Exactly. It is not be closed. Right?
Yes, sir. Yes.
Clear? Till this question it is
Yes,
clear?
sir. It is not.
So in that case, there will be no zero element also, right? Or do
Exactly.
we not even
there
go
will not
there?
be zero element, but we don't have to go till zero because addition is not defined at all. So what will be zero?
Okay, so usually when we say that zero element exists, then it will be after coming through points 1 and 2.
Exactly. Addition should be closed, addition should be commutative, then we are talking about zero element.
Okay.
Sir, I have a question.
Yeah, go ahead.
When this is a vector space, means R cross R over vector is over R. It is a real, means R cross R is a real. Then addition is usual. So why we are talking about now a different type of addition?
If you want, you can tell in Hindi also if you are feeling.
Means ये आपका जो वेक्टर स्पेस है वो R cross R है, right? R cross R है, that is a real space.
इसमें R cross R नहीं है, ये R cross R का एक सबसेट है.
No, okay, subset is also real.
Horizontal line है, x-axis का horizontal line है, x, y.
So basically, see, there are many examples of vector spaces. Okay, over R2 or in subset of R2, we can define whatever the addition we like, and we can check whether it will be vector space or not. The usual one is the standard one. R2 with coordinate addition and scalar multiplication. That is the standard one.
Hello.
Okay, that is the standard one. Now, in this case, I am giving you another example where the addition and scalar multiplication is not standard. This is what I am defining, and I am showing you that this is also can be a vector space.
But we are just forcing the structure on this.
Exactly, we are giving a structure on that. Yeah, we can do that. That's why these axioms are important.
Okay.
Till now, you only know R2, you only know coordinate wise addition and only know coordinate wise multiplication. Right? Till now, you only knew that. But this vector space, once you know the axiom, you can say that we can, we can play around with this addition. We can play around with scalar multiplication.
No, actually, I am busy. I am actually working. I am working. If I
Krishna, can you mute?
Meeting actually. Is it
Krishna,
okay?
can you mute?
Next time. Okay.
So can you mute all?
Yeah, okay. So is it clear? I mean, you are talking about usual addition and scalar multiplication. Okay, that is fine. That is already a vector space. That we know. But we can define our own addition and scalar multiplication to
We are
make a vector space.
superimposing some structure on this.
Exactly, we are imposing some structure on that. Exactly. Because we want to deal with this kind of data also.
Okay, thank you very much.
There's maybe some cases.
Sir, can you explain it graphically? Means how it will show.
I have already drawn this graph. No, this is y equal to 1 line. This line. if we take 2 points and do this addition, like we are basically adding the only x coordinates. We are not checking anything on y coordinate. So it will always on this line.
Sir, and what if we have a z coordinate too? Can you just show that diagram too?
I will come to that. So till R2, is it clear? Whatever is happening?
Yes.
So
Sir,
one small doubt. How to differentiate, for example, if we have R1 and scalar, so how to differentiate means now we are
Krishna, I will suggest you check R on yourself because I have started with R. Okay.
Oh.
You check R on yourself, and if you have doubt, you just come to the next live session and talk with me. Okay. Is it clear? Because R is more easier than this. You just check yourself. What happened if the vector space is R, only R, not R2. Okay. That will also be a vector space that I am telling you. Okay. Okay, great. So this is okay, right? This is fine till this portion, right? Anyone has doubt?
Yes, sir. Fine, sir.
Okay. Okay. Now for R2, R3, I mean there is nothing special. We are taking 3 coordinates x, y, z, and for Rn basically n coordinates x2, x3. We are generalizing this. And again, similar, the standard addition is basically coordinate wise addition. I mean, if we add, so I am taking in Rn, that will be better. So 2 vector. What is the coordinate wise addition? X1 plus Y1, X2 plus Y2. This is coordinate wise addition. Dot dot Xn plus Yn. And what is your scalar multiplication in this case?
Cx1 plus C.
So this is Cx1, Cx2, dot dot Cxn. Clear?
Yes.
So this will be a vector space with respect to this addition and scalar multiplication.
Yes.
Okay. Any issues till this point? So I want now
May
someone.
I ask, sir, may I ask just one question? Supposing
Deepa,
we
before you
define...
ask one question, Deepa, before you ask one question.
Yeah.
Deepa. Before you ask one question, I want you to summarize what I have said till now. Can you just make a brief summary of that?
Of just the last one or the whole of it?
What a vector space is?
What I understood of vector spaces is basically it involves 2 functions, the addition and the scalar multiplication. And if that is satisfied, then we look at the 8 axioms. 4 of
that
vector
is
addition.
What is satisfied?
If it's closed with respect to both
right.
of them. If it's
Right.
closed with both with respect to vector addition and scalar multiplication of the vector, then we say, then we look at the 8 axioms, 4 of the vector additions and 4 of the vector multiplications. That's what I understood, which include the commutative, associative, and all that.
Correct. Okay, you ask your question. What is your question?
Sir, supposing we say that the vector space is over, say, R3, then in that case, supposing we get a vector which is an R2, that's say 2, 4, would that
is
be
not inside R3, no?
It won't be, right? And then if we have, supposing an R4, say 2, 4, 3, 8, supposing, that would also not be in R3, right?
No.
So it will not be in the vector space at all.
No. So when we are talking about R3 and R4, there should be 3 coordinates. There should be, if you're talking about R4, there should be 4 coordinates and so on.
Okay. Right? That has to be met in every case.
That has to be, yeah. Okay. Yeah. So it is clear till this point, everyone?
Yes, sir.
Can you explain the additive inverse? One more example.
Yes, sir. Clear till this point.
Praveen, can you repeat because your voice is breaking?
Sir, can you explain me one more example of additive inverse?
One more example of additive inverse. Okay. Okay, fine. Say I am taking this example. So let's talk in R3. Okay. X, Y, Z, such that all these are in R.
PLM.
Okay. We are saying usual addition and scalar multiplication. I am giving you an element 2, 3, 0. Praveen, can you tell me what is its additive inverse?
I think.
First of all, tell me what is 0 here? What is 0 here?
3 and 0.
So what is 0?
What is 0?
0, 0, 0. Yes.
0 is 0, 0, 0, right?
Yes.
Visual addition and scalar multiplication. Coordinate wise addition.
So minus 2, minus 3 or 0.
Exactly. Minus 2, minus 3.
3 and 0.
Okay. So basically, basically you are doing what? If you have this element and your 0 is the usual origin and you are doing with usual addition and scalar multiplication, you have to take the negative of that, just minus. So if you add this x minus x, you are getting 0, y minus 1 getting 0, z minus z getting 0. So this is your additive inverse. Is it clear?
Yes, sir.
Okay, great. Okay. So basically, we have done till, vector space axioms and what a vector space is. At least we have understand that thing, right? So, yeah. So, can you use, all of you have your mobile phone in your hand, right?
Yes, sir.
So, can you see the screen?
Yes.
Now something is going on. So can you get this code and Menti, and I have asked 2 questions here about yours so that I can get who are attending the session. So can you just answer this? Then
what we have to do, sir? What
so go to this menti.com.
It is not visible.
We can't see it, sir. It's not visible.
Okay. 1 minute. Is it visible now?
Yes.
So go to this menti.com and use this code. You will see a place where you have to enter the code. And I have asked 2 questions there. Just fill that.
So we have to do it via mobile
can you
or
paste
desktop?
this thing in the chat section so that it will be easy for us to access? Yeah, just paste it in the chat section.
So we can also do it via desktop now, sir. It is not necessary for us to switch to mobile.
Yes, we can do it through desktop also.
Some of you have writing something in chat, but you can ask me directly, okay? Because I am not following the chat. Okay, you just fill this. So that will give me a.
So they're asking for a roll number.
Roll number and whether have you done this linear algebra before or not.
Sir, it's asking the presenter has to show the next slide.
Roll number is like whole email or simply the ones, the numerical part?
Not mailed, only the numerical part will be enough.
Okay, sir.
Sir, I have entered the roll number. It says that the presenter, please wait for the presenter to show the next slide. So,
but after roll number, there is one question. Have you answered that?
Roll number.
Whether have you done the linear algebra course before or not?
Yes, sir, I did.
Okay. Then wait for 1 minute. We will start. Okay. So I am seeing 35 have replied here. So we are going to.
So in second option, linear algebra, before this, what I choose the option no or yes?
That depends on you, no? Have you done any linear algebra course before?
Yeah.
Like from anywhere.
Then you should press yes.
Okay.
Yeah.
So there is no question inside Menti.com.
That is the question, no?
Refreshing the slides, nothing is happening there.
Yes, sir.
You have put your roll number there? Roll number and...
Yeah, sir.
Then wait for a second. I will go to the next slide and you will see the question.
Mentimeter.
Yeah. Yeah, Praveen.
So can you transfer the please enter the code?
This is the code 98713508. Okay.
Sir, meanwhile, why that's
let me mute all, then
Please
I can
asking,
hear you
please wait
properly.
for the
1 minute, 1
presenter
minute.
to show the next slide.
I will show. Yeah. So I am going to the next one. Okay.
Sir, it says code could not be found.
Yeah. So can you see this question now in your Mentimeter?
Yes, sir.
So there are basically four main topics in this week: vector space axiom, subspaces, linear dependence, and independence. Now you can select more than one. So this is just to get an idea which you are feeling difficult. Now we have already discussed vector space axiom. So I hope that will be seeming little bit easier to you now.
So the other topics, will it be covered, like the spanning?
Yeah. I am trying to cover
today or next time?
Let's see how far I can go today. Okay.
Please do not extend the session beyond 10 p.m.
Maybe no.
At least please discuss the first question of practical findings.
Sir, please arrange another session tomorrow 6 p.m.
On Thursday there will be a session at 6 p.m. Okay, Thursday.
I don't think a spanning set are in the week 3.
But it will be required. Okay.
Okay.
To discuss linear dependence and independence, we need them.
Yeah.
Okay. So this is the question. I hope all of you have pen and paper with you.
Yes.
Yes, sir.
We are going to discuss this question because we have already seen what we are doing. So this is the same type of question. The set is 1, minus y. Okay, with usual addition and scalar multiplication, and you have to say which of the options are true. So first of all, you write the options. 1, 2 is it belong to V. 2, 3 V is whole R2. 1, minus 5 and V2 is 1, 7 implies V1 plus V2 inside V. So here remember, with usual addition and scalar multiplication we are talking about. That means coordinate wise addition and multiplication. Okay. Then 1, 9 inside V, C is any real number, is C, V inside V. And for all V belongs to V, CV belongs to V, only for C equal to 1. So you have to choose which options are correct. Okay. Once you read the question properly, I will go to the next slide so that you can input your options here. Then I will discuss what will be the answers.
So is it a MSQ or it is a MCQ?
Yeah, it is an MSQ.
I'm not able to check the options.
Check the option first. See the question right in your pen and paper. Then I will go to the next slide so that you can put your answer. Okay.
So we have to check 8 axioms for each option, right?
No, this is not a question where you are asking that it is a vector space or not. See the options. You have to check only the options. Okay. This is not a question where I am asking you whether it is a vector space or not. That will come later. First check which elements are in there. Is it whole R2 or not? This thing. Okay. So I am going to the next slide so that you can give your answer. You have seen the question properly?
Sir, 1 minute, sir. We will write down the answers.
Just write down the options. Okay. So I think I should go to the next slide. Okay.
Time. Few minutes.
Yeah. Now you put whatever options you are willing to choose. Option 6, I am saying.
So we can select
Option
only
1, option 3, option 4.
Sir, we only have option to select one of them here, apparently.
Oh, is it?
No.
Yeah.
We
Yes.
can select multiple.
But it selects
No, sir,
only the
we
last
cannot
one which
select
is selected.
multiple.
No, there is no multiple.
No. Only one we have to click.
Only one.
Okay. Then there is some issue with the setting. Okay.
It is showing multiple.
Okay.
Go to the question slide, please.
Sir, can you go back to the question, sir?
I will go back to the question, but first. That's why I wanted you to write the questions first.
5 and 6 both.
5 and 6 you are saying? Okay. Okay. So now let's discuss what the answer is. I will come back here and I will discuss. So this was the question. Okay. Can you see the question here?
Yes, it is
Yes, sir.
visible.
Yes.
Okay. So first of all, is 1, 2 inside V?
No.
No.
Yes.
No.
Yes.
Yes.
So those who are saying no, can you give me a reason why no?
Because V is given 1 comma minus y. And there it is 1 comma 2. So minus y is not equal to 2.
But if I take y to be minus 2, then?
Then it will come to
Then it is, right?
Yeah.
Y can be any real number, no?
Yes.
So it is inside V. Okay? Any doubt?
No, sir.
So basically here is nothing different between 1 comma y and 1 comma minus y. That's the point. First point. Okay. Is 2 comma 3 inside V? So option 1 is correct.
No, it is
No.
No.
Option 2 is not correct. Option 2 is not correct. I give one third.
Mute all because there is a very disturbance.
Mute all, sir, please.
Okay. Okay. If is V equal to whole R2?
No.
No.
False.
False.
Yes,
Obvious.
true, no, sir.
Why?
Because it's a tuple, no pairs, no?
But is all elements of R2 are in there? Because you have
No.
already said that 2 comma 3 is not there, no?
Yeah, correct.
So it is
Okay.
not whole R2. It is a subset of R2.
Okay, sir, got it. Thank you, sir.
Yeah. So it is not correct. It is cross. Now see V1, 1 comma minus 5, it is inside V. This is also inside V. But is the addition inside V?
No, sir.
No.
Because we are using usual addition, right? That means 1 comma minus 5 plus 1 comma 7. What is this?
2 comma something.
2 comma 2.
2 comma 2. Right? So this is not inside V. This is
It should be 1 comma 2.
So there was this confusion. Like if the question says usual addition, then only do the usual addition. Else,
exactly. Usual means standard, coordinate wise. Otherwise, it will be given what the addition is.
Otherwise, it is true, right?
No, if addition is given, then you have to check what is addition, right? Depending on that. Okay. Okay. Option 5.
But in same vector space, it's okay, na sir? 1 minus 5 and 1 7.
If addition how I was defined, then it should be inside V. How I was defined, but it is usual. Okay. Yeah. So V is 1 comma 9 and C is any real number. Or C into V.
Is it true?
No, sir, wrong.
Why?
Because usual scalar
multiplication.
multiplication.
If C is 5, then it is
So what is 5 into 1 comma 9?
5 comma 45.
So it is not inside V. Correct. So this is also not correct. And the last one. For all V belongs to V.
Correct.
It is also correct. Only for C equal to 1. When C is 1, only when it will be correct. Right?
Yes, sir.
Sir, could you please explain the first option? Means I did not really get it. That 1 comma 2, and why are we not considering it 1 comma minus 2 as the right option? And why 1 comma 2 would be the
So
right option?
Y is any real number, right? So if I take Y to be minus 2, what is 1 comma minus Y?
It is plus.
Okay.
1,2, right?
Okay.
So this is inside the real number. So this
Okay, I
is
got
inside.
it. I got the logic now. Yeah. Thank you.
Okay.
Can you explain this option number 3 once again? Option 3.
Option 3. So 2, 3 is not inside V, right? You have already said that. So it should not be whole R2, right? V is R2 means what? All the elements of R2 should be inside V. But that is not the case, right? Even 0, 0 is not there.
But subset is fine.
It is a subset of R2. It is,
subset.
it is a subset of R2. It is not all R2.
Sir, a little bit slower, please. I'm not getting it.
It is a subset of R2. It is not whole R2, right? What is equal R2 means? Any element of R2 should be inside V, right?
Yes, sir.
So can you give me one element of R2 which is not inside V? You have already given me 2, 3.
Yes, 2, 3.
Right? 2, 3 is inside R2, but it is not inside V, right? So these two should not be equal.
It is in
right?
R2, but it is not in V. Right? Because
Exactly.
if it has to be in V, then it should be 1, 3.
Exactly. V is a subset of R2, not equal. Okay, clear?
Yes.
Yes, sir.
Okay, great. So this question is clear to everyone, right?
Yes, sir.
Yes, sir. Yes.
Okay, great. So let's go to this one. So I will show this question here. Okay. Can you see this question? The same vectors, the same set we are taking.
Yes, sir.
Now with usual addition and scalar multiplication. So see the option properly. And then we will talk about this. So by seeing the question, can you tell me whether any of the option is making any sense? We are talking about usual addition.
No, sir. Yes, sir. Option 4 it is.
So basically usual addition means addition is not closed even, right?
Yes.
Yeah.
So addition is not defined there.
No option is correct, sir.
Sir, what is the meaning of zero element?
Because addition is not defined properly, right? So zero element does not exist here.
Exist.
Correct?
Correct.
Yes.
Yeah.
Sir, why doesn't the usual addition exist? Can you repeat that?
So usual addition means what? Usual addition means coordinate wise addition, right?
Yeah.
So if you addition, suppose 1, 2 and 1, 3, both are in V, right? Now with respect to usual addition, what will be the output?
1, minus 5.
2, 1,
5. 2, something. So it is not inside V, right?
Yeah.
So addition is not closed.
Yeah. Okay.
So only in case if it would have been a vector addition and not a usual addition, then only option number 3 would have been correct.
No, vector addition, this is
Not
also
vector
usual addition is also vector addition, but with respect to this addition, this set, on this set it is not closed. That's why we cannot talk about addition in this case. But if we define addition how I have defined earlier, then we can talk about this zero element or all this.
Well, sir.
So what is a zero element? Is it 0, 0? Something like that?
Vector element is not
The
defined.
question now. Is zero element exist here?
No, sir.
Addition is
Because
not
addition
defined.
is not closed. Addition is not defined.
Yes.
So how can zero element exist? Zero elements means what? The element, if you add with any vector, it will give you the same vector.
The same vector.
I have discussed, right, earlier. But it does not mean that zero element should always be 0, 0. It should depend on the way you are defining the addition. Okay? Clear?
I am not getting why zero element is not present.
First of all, tell me, is this addition, defined, well defined? Is it closed? Usual addition, is it closed?
No, sir.
No, sir. It is not closed.
Why not, sir?
That is clear to
Should be
you?
closed.
Because one
condition are
will change,
not
sir.
used.
No, he is saying it is closed. Who is that? Can you tell me your name?
Sir Naveen.
Navi, how this usual addition is closed? If you take 1 comma 2, 1 comma 2 is inside V, right?
Yes, sir.
Yes, sir.
1 comma 3 is also inside V.
Yes, sir.
What is the usual addition give me?
2,5.
2 comma 5, right?
Usual addition.
Usual addition means coordinate wise addition.
Yeah.
So 2 comma 5 is not inside this set, correct?
Yes, sir.
One is constant, there cannot come any other.
Exactly. So addition is not closed here. So zero element does not exist here because existence zero element depends on the existence of addition first, right? So zero element does not exist here.
Sir, if zero element does not exist, then also inverse element also not exist.
Not making sense. Exactly. Inverse also does not exist.
We have to go
Option 5 is also correct.
First we check for addition, then we move forward.
Exactly. That's what. Okay.
So
So option 5 is also correct. Option 6 is also correct.
156.
Right? 156.
Sir, what is zero element?
Zero element does not exist. You are asking, I mean, in general, what is zero element?
Yeah.
So Priyanka, were you present from the beginning? No, I think, right?
I was.
So I have discussed what zero element is. Zero element means if you add any vector to that element, you should get back the original vector, right? I mean, V plus that vector should be V.
Okay.
No, question is solve.
Okay, so I think I have already taken poll on that. So I am moving forward, okay?
Sir,
yeah.
If we did not define V as some set, so then the zero element will exist under usual addition, right?
I mean, V should be some set. I mean, that is the first condition for vector space. There should be a set.
No, it's just X comma Y belongs to R, something like that.
So basically the whole set. You are saying R2 or R3.
Yes,
right?
anything, R2, R3, anything, and we don't define it particularly, and we just say some X comma Y belongs to R, and under usual addition or multiplication, then the
that is your
element
R2. That is your R2. Okay, what you are saying is basically R2. Yeah,
yes,
go ahead. Yeah.
Yes. So then the zero element will exist, right? The zero element will be 0, 0.
Exactly. Yeah. Correct.
Okay.
Okay. Someone have placed option 4, but option 4 is not right. Okay.
Yes, I have ticked the option 4. What I want to say is when addition is not closed or multiplication is not closed, then there are then we don't have to check any of them.
Then you don't have to check any other LCM.
And no zero vector, no inverse.
No zero vector will
anything
exist.
doesn't make any sense, right?
Exactly. And once zero element does not make any sense, then inverse will also not make any sense.
Okay. Right.
Sir, please show the question.
I will show the question. So this is the question.
Can I ask a question on what you just said? If it is X comma Y and X comma Y belong to R, then zero element exists all the time, right?
With usual addition and scalar multiplication, yes.
Even with usual addition also there is a zero element, correct?
Sir,
I mean with usual addition and scalar multiplication there is a zero element. So I don't know for other addition and scalar multiplication because I have to know what other addition and scalar multiplication is.
Right.
Sir, why the inverse element of why option 4 is not valid?
Because zero elements does not exist, then how can inverse element exist? Because existence of inverse elements depend on the existence of zero element. No? V plus the inverse element should be the zero element. Now zeros does not exist. How can inverse exist?
Zero element and inverse element are result of vector addition only.
Exactly.
So continuing on this,
I am muting everyone for once because I am getting very noise. Yeah. Now you can unmute one by one. Okay.
Yeah.
Sir, I have a submission, sir. Sir, can we discuss the practice ascending question number 1? It would clear a lot of doubt.
No, I will not solve practice question number 1. I will just discuss how I am discussing. Yes, even if you cannot solve it, then we can solve it in the next session. Okay?
Sir, what is option 6, sir? Option 6 is correct.
You tell me option 6 whether it is correct or not.
Yeah, it is correct.
It is correct, right? Because zero element does not exist means we cannot talk about inverse element for any element.
Can we conclude that zero element is the one where the mirror happens for the inverse? Means it is the
mirror.
point.
I mean, what is mirror?
Means inverse. Inverse means, for example, if
so that is
mirror.
When you we are trying to reverse it. If there is no zero element, then we cannot reverse from that point.
When you use the word mirror, you have to define mirror from where.
That is zero element. That is zero element.
No.
With respect to one element, how can you mirror this? You just remember this definition. No, this is not difficult. Why you are going to mirror and all those things? Take an element, you have to add another element so that you get back your zero. That is the point. If you have 5, what you should add with it so that you get 0, that is -5. Okay? Is it clear?
Yeah. Can I come back to my earlier
Can you
question?
just draw the three tuple vector, like how to draw that?
In 3D plane.
Yeah.
It is a point on R3. So there is 3, this is X, this is Y, this is Z. So there is a point, suppose 1, 2, 3. This is the point.
So how to define, how to be calculate it? I didn't get that. How to ascertain that that point is 1, 2, 3, like in a 3D plane?
So in X-axis you have to go 1 distance. Here it is 2 distance. So this is a point 1, 2 on XY plane. Now you have to go move upward 3. So this is 1, 2, 3. So let's make it here.
Tuple can also have 4 elements as well.
That I cannot draw basically. So is it clear?
So sir, in this question which we are discussing?
Yes, sir.
Is it clear? This is the point 1, 2, 3.
Yes, sir.
Yes.
At the end point of the cube.
So first we have to take XY plane and then just extend it to Z plane, right?
Move upward. So think it as a you are inside a room, right? So
but then what about negative elements? -1?
That will be inside, under, in the opposite direction.
Sir, did not get. Can you explain?
Yeah. Okay, so let me show you something. You can do it yourself also, okay? Type just GeoGebra 3D.
Sir, actually on GeoGebra now I'm not able to understand properly, like.
Okay. So I will tell you. Okay. So you can see this. This gray area is your XY plane. Okay.
Okay.
The red axis is your x-axis, the green axis is your y-axis, and this blue axis is your z-axis. Okay.
Yes.
And see what is going below, that is your negative z-axis. Okay. Is it clear? It got stuck.
Praveen, can you please mute yourself?
Sir, actually when it's quite moving, it's very tricky to understand. Like.
Where?
No, like, I mean, it's very tricky to draw, right? Like.
I mean, obviously it is difficult to visualize, but anyway, 3D you can get, no? So that's what I am saying. So what if I want you to describe some point on your room? That where is your fan?
Just take -2, 0, and 3, and just like, can you just draw it for me?
0, 3. Yeah, that point. Yeah.
-2.
So an x-axis you go -2.
Okay.
Y-axis you have not gone anywhere. So in this blue axis, via this blue axis, you are just staying there itself. Now you move upward 3.
Acha. Okay, sir. Yeah.
Okay.
Thank you. Yeah.
You can show this to her by just moving the plane around.
Sir. Yeah.
But it is getting stuck. That's why I don't want to move it.
Yeah. It's clear now.
Clear, no?
Yes, sir. Yeah.
So can I ask one related question, sir?
So basically, what is going here? So if you draw this plane, I think, So I have drawn this y equal to 0 plane. Okay. So your point will be on that plane. Can you see? Is it clear? Hello.
Yes, sir. Yes, sir.
Am
Yes,
I
sir.
audible? Yeah.
Yes, sir.
Yeah. So this point will be on y equal to 0 plane, because on y-axis we are not moving at all. Y-axis is 0. Okay. Okay. And great. So yeah, where are we?
Sir, can I ask one question, sir?
Yeah, go ahead.
Sir, the concept of a tuple having more than 3 elements. I guess
that doesn't depend. It can be 2 elements, 3 elements, 4 elements.
it can be any number of elements.
N tuple basically.
N
Depending on
tuples. I guess we use this concept only to deal with deal in the string theory, I guess.
No, there are many applications of this.
Also in string theory, na sir?
String theory, there is application, but there are other applications also. String theory is, I mean, that uses many more things. Many more things they are using.
It helps us visualize, multi dimensions.
Yeah, correct. But I mean, don't have to go there also. I mean, RN you will get in your any data science course.
It can have applications in many ways.
Many places. I mean, where more than n variables are required, more than 2 variables, more than 3 variables. There can be problems like that in real life, right?
As far as its physical significance is concerned, I was thinking.
So you can say.
I mean, suppose I am saying, suppose you have to. What should I say? You have to deal with the data where you need to know the temperature of a place, the geographical position of a place, the weather, the temperature, weather, I mean everything, the speed of wind at that place. All this is your variable, right? So there are more than 5-6 variables what I am talking about.
Yes, sir. Yes, sir. We have to deal with all of them.
Sir, can I ask one question? But it is not related to this question. My question is related to the mock test question number 7. I couldn't get it, the question.
Sir, I have one question
related to this.
See, for mock test, I mean mock quiz, we are going to, another special live session. Okay, that I think was mentioned in announcement. So in that we will discuss everything. Is that fine?
Okay, sir, I have one thing related to this question. So if you permit, I'll ask. So had it been a set wherein we have this set defined, and it would be not have been a usual addition but a vector addition. So all these conditions like 0 element would have been existed in V. Second, inverse of element 1, 5 would also have existed, and the inverse of any element would also have existed. So entire option would have got reversed had it been not a usual addition, right?
Yeah, I mean, if I define the addition as I have defined here.
What we have defined earlier, like x comma 1 belongs to the real number. So in that case, all the 3 options would have been negated, what we have selected right now, right?
Yeah. So if I define addition, 1 minute. If I define addition like this.
Here, if you can mute yourself.
If I define like this, then it will be proper, no? If I define like this, then you know what 0 element is and what inverse is. I mean, 0 element will not be 0, 0. Remember, that is not the 0 element.
Right.
But inverse will, inverse will be something like this. Okay.
Yeah.
Sir,
thank you, sir.
Hello.
Sir, when will be the next session?
Thursday
at 6 p.m.
Thursday at 6 p.m. Yeah.
Okay. Thank you, sir.
Yeah. Okay.
So I guess the concept of vector space is discussed in in Avengers 3 Endgame.
Hello.
I don't watch Avengers, but I really don't know.
And they have to go to search in space, and they use the term vector space to go searching in space, because everything is moving now relative to each other.
Oh, okay.
So would you be discussing any new topic today, or are we going to?
So I am planning to discuss new topic, but let's see. I want to discuss the subspace also a little.
Sir, can I ask a small question?
One small question, sir.
Sir, hello.
One by one. I am here.
Sir, one small question which I want to ask is, we have to always look at the definition while finding whether it is a vector space or not. We have to keep definition in mind, right?
Yeah, exactly.
While taking the axioms and all that.
Yeah.
Okay.
Yeah. Then.
सर लास्ट वाले क्वेश्चन में सर ये 1 2 3 कहाँ से आया? Was it related to the question और कुछ और सवाल था? या which you describe this XYZ
नहीं, ये अलग सवाल था कि 1 2 3 पॉइंट कहाँ पे है R3 पे.
ओके ठीक है, थैंक यू. Nothing else. Thank you.
Yeah. Anyone else?
Yes, sir. Can you please go to the options?
This one?
Yeah. Sir, here we have the set 1 comma minus y. Zero element exists if that was added with minus 1 comma plus y. But minus 1 comma plus y does not belong to the R2. So we
No. That is not the point. See, here it is written usual addition. What is usual addition? Usual addition is, suppose this element. Is this element inside the set 1 comma 2?
No.
Yes.
No.
Why not?
Yeah. It is there.
Why it can be minus 2, right?
Yeah.
Okay. And 1 comma say minus 5. This is also inside the set?
Yes.
What is the usual addition?
2 comma minus 3.
So is this set inside V?
No.
No, this is doesn't belong. So with respect to usual addition, this addition is not closed. Can I say that?
Yes, sir.
So once addition is not closed, that means addition does not make sense here, usual addition. That means we cannot talk about zero element. That's why zero element does not exist.
May I ask a continuation of the same explanation, please?
Yeah, go ahead.
Instead of saying 1 comma minus y, I say x comma y belonging to R. Then can I say, even if I say usual addition, it is same as closed?
Then it is closed, no? That is your R2 basically.
That is R2.
That is R2.
That is R2
X
and that
y?
is, yeah.
This is you are talking, right?
Yeah, this is what I'm talking about. In this case, even if I say usual addition, it is the same as closed condition, right?
Exactly.
Okay.
The usual addition,
yeah.
What I have started with basically.
Okay.
Remember x1 plus x2, y1 plus y2. So in this case, 0 comma 0 is your zero element. Yeah. Any other doubt till the definition of vector space?
Suppose it is given usual addition and usual scalar multiplication. Then we can write the definition like x1 comma y1 plus x2 comma y2 is equal to x1 plus x2 comma y1.
Exactly. Coordinate wise.
We can design that definition for just for keeping.
That is the usual one. That is the usual one, right?
Yes.
Yeah. So if this definition, at least this vector space definition is clear, I think half the job is done basically.
Yes,
if
sir,
it is still not clear, then it will take much of your time.
That is why I was trying to discuss the practice assignment question 1, option 5.
You solve it, Naveen. You solve it yourself. I am not solving your practice assignment. You solve it. If you have any doubt, you ask to discourse or.
Sir, please upload all the notes in the book.
Yeah, I will do that. So yeah. So should we go ahead or should we stop here?
Sir, can we discuss this on a fresh day?
Sir.
Yes.
Stop,
I think we can start with a fresh mind.
Okay, sir. A request. Thursday, 6 o'clock. Can you postpone it to 7:30 something?
Actually, from 8, I think there is a Python session. So some of you may join Python session, right?
Yes, sir.
Yes, we are planning to 6 to 8.
Can you arrange?
Yes, sir. So please postpone it because 6 is like a very prime time for office people.
No, 6.
Sir, actually we are enjoying the session, but I don't know about that.
When will
And if we miss the next session, then I don't think we will be able to understand the rest.
No. The thing is that if we can't understand third week, then it is very difficult till 9th week.
Sir, are you coming in the
that's
next?
why we are trying to convey more about this third week.
So can you arrange?
Are you coming in the next session?
6 o'clock.
I may not come in the next session. Shubham will take, I think.
Sir, actually I had some conceptual doubt in aage wala topic, so I just wanted to discuss.
Right.
Sir, do we have a session tomorrow, sir?
Tomorrow
Yes,
is
can you
not possible, I think.
arrange one session tomorrow, sir?
Same time.
Tomorrow.
8 to 10.
Same time, sir.
Sir Shubhasish,
Time 8
sir,
o'clock.
actually, when will be your next session?
Okay, let's see. I can take Thursday maybe. Let's see.
Yes, sir. Please do that. It will be very helpful.
Yeah.
But not 6 o'clock.
I mean, if you want, I can continue for some time now also, if you want.
Sir, yes, do please
actually,
continue.
Yes, sir, please
Yes, sir.
Please
I don't have
date and
any
time of
problem if you continue. It will be
Yeah,
great.
so I will continue for some more time.
Yeah, at least for them who are interested, you can, if you can continue.
Other people can see it in YouTube also because
Yeah,
it is
recording.
recorded. Yeah.
Correct.
Yeah. So let me finish till at least subspace. Then it will be
Yes, sir.
easier.
Sir, please date and time of next session.
And sir, if time allows, you can take some doubts also.
Yeah, right. Date and time for next session is Thursday 6 to 8. That is for now.
Evening or morning?
No.
I think you can see on the calendar now.
So morning, why can't you do, sir? What is the issue actually?
No issues, I think.
Yeah, then 6 o'clock in the evening is too hard.
सर morning में रख लीजिए.
Morning is better, no?
Morning, okay, मैं देखता हूँ.
Morning at what time?
Yes, sir. जब भी रखिए, लेकिन आप आइएगा week 3 वाले.
6 o'clock in the morning.
Okay, so let's discuss this. Date will fix later, okay? Yeah. So vector space is clear. Now, when we are discussing our set, we discuss our subset also, right? What is a subset of a set? Suppose I have two sets, A and B. I am saying A is subset of B. What does it mean?
Means A contains all the elements that is there in the B.
Basically, all the elements of A are inside B.
Yeah.
Yes.
Right?
Yeah. So it's part of the B group.
Exactly. So B is the bigger one, A is inside that. Right? This is the diagram we can visualize. Similarly, in vector space, we can talk about subspace. Okay. So what does it mean? So I have vector space V. Inside that, so vector space V means it's a set with two operations, plus and there is scalar multiplication. Right? This is my thing. Now, when I am talking about a subspace, that means I have a vector space V. Inside that, I have a subset. First of all, subset is needed. I mean, all the element of W should be inside V. This is the first condition. Okay. Now, vector space comes with addition and scalar multiplication. What does it mean? So, it means, first of all, zero vector, the zero vector of V. There is also a zero vector in V, right? In the axiom, we have checked that. Now, that zero vector should be also inside W. Okay. So, the addition which I am talking about in V, the same addition will work inside W because the elements are same, right? Whatever the elements of W, those are basically elements of V. So, addition makes sense there. So, only thing we have to check is, first thing is zero vector should be inside W. The zero vector of the original one should also be inside W. So, zero vector should be somewhere here. Right? Now, the second and third thing is really crucial. That means if we take two vectors, V1 and V2, if we add these two, then the resultant vector should be inside W itself. Now, what does it mean? So, this is my V. Okay, let's draw the picture a little bit here. This is W. So, I am adding two vectors. This is W1, this is W2. Now, we know this W1 plus W2, it is inside V, that we know, right? Why? Can someone tell me? Why this is inside V?
Because W is inside V.
Because
W is inside W means what? W1 is inside V, W2 is also inside V, right?
Yes.
Because W is a subset of V, right? W1 and W2, they are inside W. Now W is a subset of V, that means both of them are inside V. Now, when these are inside V, the addition, due to the closure property, which we have discussed, the addition is inside, I mean the resultant vector is inside V, that we know. But if W has to be a subset, the addition should be inside W itself. Okay? Is it clear? So the closure thing should be inside W itself. Whenever I am taking two elements from W, when I am adding them, I know that the resultant is inside V, but that is not enough. The resultant should be inside W itself. Okay?
So we can say
And
that W
similarly
is the
for the
new
scalar
V.
multiplication, if I take any scalar, I multiply with the element of
Sir,
W.
so this is for every V1 and V2?
Every V1, V2 inside W, right?
Inside W, yeah.
Inside W,
Yeah.
this is important.
So we can say that W is new V.
W, so basically what is that? Basically this new set, new subset, this is itself a vector space. Exactly what
yes,
you are
sir.
saying.
Yes, sir.
This is becoming itself a vector space, but in this case we don't have to check all the 8 axioms because that we have already checked for V. We know for the elements of V those axioms are hold. We only need to check 3 elements, 3 things: closure property of addition, closure property of scalar multiplication, and 0. If we check these 3, we are done, because other will obviously satisfy because they are element of V. So we know the axioms are satisfied there.
So in addition to check if whether it's a vector space or not, we have to check also 0. Vector.
Only these 3 elements we have to check. These 3 things.
Sir.
0 is there or not, and addition and scalar multiplication are closed or not. Only this thing we need, because other elements are obviously there. What was the other thing? Commutativity, right?
Yes, so
This W1 and W2 are element of V, so they are commutative. What is W1 plus W2? That is same as W2 and W1, right? Because they are inside V, so we don't have to check it further.
Yes.
So
Then what about inverse? What about inverse, sir?
If we
that
have
will
checked
be also
0,
inside
then
W, no?
inverse,
For
inverse will
this
be-
2 property. That is also inside there.
Okay, because it's a addition. Okay.
Exactly, because it's addition, correct.
Okay. Okay.
Right. So only these 2, only closure property you need to check. Closure property of addition, closure property of scalar multiplication, and 0. Whether these 3 are there, only these 3 have to check for the subspace.
Sir, I'm still a little confused. I'm still a little confused on inverse. How can we be sure that if supposing V and its inverse, how can we be sure that its inverse would be in W?
Okay, great. Suppose W1, I am explaining. Suppose W is inside W, right?
Yes.
And its W prime is its inverse. This is inverse of W.
Yes.
This is inside W. Inverse of W, right?
Right, sir.
Okay. Now inverse means what you know? W plus W prime is 0.
Is equal to 0.
Right?
Yes.
0.
This you know, right?
Yes, sir.
Okay. Now this is inside W. This is inside W, you have already checked.
Right, yes, you have already. Yeah.
Where this should be.
Yes, sir.
You can take this on the other side, right?
Yeah.
Yes, sir.
W prime is basically 0 plus minus of W, right?
Yes.
Now this minus W means what?
Belongs to
This
W.
is scalar multiple of W, right? Minus 1 into
Yes,
W,
sir.
right?
Yes,
Now
sir.
W is inside W, so scalar multiple of it is inside W for the closure. 0 is
Yes,
inside
sir.
W, so this is inside W, this is inside W, so
Okay.
addition is inside W. So
Yes, yes, sir. Thank you so much. Thank you.
yeah.
Yes, understood, sir.
Yeah, good question. That is good question. You
zero
should ask
element-
that.
If
Yeah.
zero
One
element
question,
is-
sir.
Thank you, sir.
Yeah. Yeah, go ahead. Yeah.
If zero element is there, means inverse is there. Can you conclude like that?
Yeah, basically that's what I have proved. No?
Yeah.
Yeah.
One question, sir.
Okay. Yeah.
Hello.
Yeah.
Hello.
Go ahead. Yeah.
Sir, why do we need the concept of subspace when W and V are going to be the same sets?
Okay. So can you tell me why we need the concept of subset to begin with?
Subspace. Yes.
Subset.
Subspace. If W and V are okay.
Why we need subset? Why we have studied subset?
We are interested in a smaller set of original set.
See, suppose consider this set of all BSc student, IITM BSc student.
Yes.
Now I only, for my course, this course, Maths 2, I only need to know who have taken Maths 2, right?
Yes.
I don't need who have taken Python.
Yes.
Right? I only need that much of data.
Yes.
So I have to deal with that subset, right?
Yes, sir.
For the same property, I need to deal with this subspace.
For sanitization.
But sir,
exactly.
With these properties, sir, every element is going to be in the subspace now, sir.
No, every element, no. I will give you example. Okay. So see, suppose my vector space is R2. Okay.
Yes.
with usual addition and scalar multiplication. Standard. Coordinate wise addition and scalar multiplication. Okay. Now I am defining my W as, can I define this? Is this a vector? Is this a subspace?
Yes, sir. Yes.
Can you check?
Yes, sir.
Okay. So first of all, 0, 0 should be there, right? Because 0 is the element, 0 element here. So is 0, 0 inside W?
So you mean to say that, sir, the addition and multiplication definition can be changed in subspace. It can be different than parent set.
No, it is not different. It is same.
Okay.
It is same. It is same. Addition and scalar multiplication should be same for subspace. Okay.
Then show me, sir.
So first of all, tell me whether 0, 0 is inside W or not.
Yes, sir. Yes.
It is inside W, right? So first condition is checked. Now addition. If I take two elements x, 0 and say x prime, 0. If I add this with usual addition, what I am getting? This. Is this inside W?
Yes, sir.
Yes. Then third one. Scalar multiplication. C into x, 0. What is that? Cx, 0. Is it inside W?
Yes, sir.
Yes.
So this is a vector subspace.
Okay.
So basically what is this? This is your whole R2, right? Whole plane is your R2. Now what is this thing? This is basically x, 0. That means x-axis.
Means only
x-axis. Only x-axis. This is a vector subspace. This.
Okay, sir. Got it.
Okay. Similarly, if I take any line, suppose this line.
Yes.
X is equal to y.
X equal to y. So anything x equal to 3y also I can take, but let's start with x equal to y. Sorry, x equal to y means I am writing it x. Okay. Is this a vector subspace?
Yes.
Yes, sir.
Yes. Again, you can check these three properties, you will get that. Okay. Now I want all of you to think, I will not describe why, that all the subspaces of R2, what are all the subspaces? See, this set, only 0, only origin, this is a subspace, correct?
Yes.
Only 0, 0, because it satisfies all the property anyway, right? Yes. So this is called trivial subspace. Trivial subspace. R2 itself, this is also a subspace, right?
Yes, sir.
R2 is a subspace of itself. Okay.
Sir, any value on x-axis is a subspace. So 2, 0, 3, 0.
This x-axis in this whole set is a subspace.
X-axis, y-axis.
0, 1.
Any line passing through origin will also
exactly. And the third condition is, third type is basically any line passing through
origin.
And these are all. There are no other subspaces.
It covered all.
It covered all with respect to usual addition and scalar multiplication. That is behind. Okay. So if we are talking about subspaces of R2 with respect to usual addition and scalar multiplication, there are only three types. Only the 0, 0 singleton set, whole R2, or any line which is passing through origin. These are the only three types of subspaces inside R2.
As far as we are dealing with the usual addition and
exactly, that is there. Correct. Yeah.
Then why only? I didn't understand the third part of it. The line passing through origin, basically where x and y are equal, right?
No, that does not mean equal. Any line, y equal to mx.
Okay.
What is y equal to mx?
Where we don't have a y-intercept. Y-intercept is 0.
No, this one, right? Y equal to mx line I can express like this, right?
Yes, sir.
Can you check this is a subspace or not? Is 0, 0 in there?
Yes, sir.
Yes, sir.
Yes, sir.
Yes. If I add two of them,
yes,
x, mx plus x prime, mx prime, what I will get?
X plus x prime. M into x plus x plus m.
So this is on the same line, right?
Yes.
So this is also inside W. Similarly, scalar multiplication will be also inside. So any line passing through origin will be a subspace.
Okay, sir.
And there is no other subspace. Why that is, I am not telling you now. I will tell you in week 5. Okay.
Yes, sir.
So this second condition, which is if two vectors v1 and v2 belongs to W, then v1 plus v2 belongs to W. This is always will be a v1 and v1 prime.
What does this is just a notation v1 and v2. Basically, you take any two vector from W. The addition, the resultant vector will be inside W. That is
You can call v2 v1 prime.
Anything.
Will it always be v prime? One is v and other is v prime, because the two examples you just
that
gave.
depends on you. You can call it some. This is biryani. This is chicken. That is also okay. Biryani plus chicken should be inside.
Because the two examples you gave, you have always taken prime. That's why I'm asking that.
That is a notation only.
So we can take A1, A2 as well, or A.
Yeah,
A
you can
prime.
take A, B, you can take C, D, you can take E, F, anything.
It should belong to
W. You can
W.
take cat, you can take dog. One element has cat, one element has a dog. The sum should be inside there. This is the notation. There is nothing specific.
So maybe she is confused with this inverse. Prime means inverse.
Yeah, maybe
No, she is talking about this prime.
Two examples you took. You just proved by
This
that
prime.
x 0 and
This
x
one, right?
0. Yeah, I'm saying that because both the examples you described with this prime. That's why I'm asking that.
Okay, if you don't like this prime, then I can change it. This one. Okay.
Okay, that will be any. Okay.
Anything. Okay. This is notation. Don't get confused with the notation in maths. Okay.
It could have also been a y,
no?
sir, right?
You understand the concept, right?
It could have even been a. It could have even been a y, right, sir?
Anything. Okay.
Sir, here 0, 0 is zero vector, no? In last.
You with respect to usual addition, it is the zero vector. No?
Okay.
Yeah. Okay. So this question. So I am giving you again going to this Mentimeter thing because that would give me an idea. Okay. This I think all of you have filled up, so I am avoiding this one. So can you solve this? You have pen and paper with you, I think. So this is the last question which we are solving today. So let's take that. So first of all, write this one. What is the set W? Have you written that? Have you written the question? So here I am talking about with respect to usual addition and scalar multiplication. Okay, that is not mentioned in the question, but that should be. So this is with respect to usual addition and scalar multiplication. So should I go to the next slide?
Yeah.
Okay, so I am going to the next slide. You can put your answers there. I think again you can put one answer maybe. Okay, 2 and 4 are getting the votes basically. All the options are getting the vote now.
Sir, it is a multiple. That means only one option I can tick.
No, it should be multiple select, but I think I have messed with the settings somewhere. So you put only one correct option, then we will see. We will discuss the answer. Okay, so option 1 is getting more vote. Yeah, that is clear, I think. Okay, so I am going back to the question. Yeah. So what is zero element here with respect to usual addition and scalar multiplication? 0, 0. Correct?
Correct.
So is 0, 0 inside W?
No, sir. No.
No, sir.
No is equal to 1.
No,
Right?
sir.
Because it does not on this line, does not belong to this line, right? because 0, 0, 0 not equal to 1. So 0 element exists in W. This is wrong. Correct? Is it clear to everyone? Many of you have
Yes, sir.
put this as correct answer.
Yes, sir. Yes.
No, sir. Can you please clarify it?
Okay. So first of all, with respect to addition, usual addition on R2, 0, 0 is the 0 element. That is clear, right?
Yeah. That is clear.
Clear?
Yes, sir.
Right.
Ah.
0,
Okay.
0 in
So, but 0, is 0, 0 inside W? So what I have to check? 0 plus 3 into 0 should be equal to 1. But is this 1?
Yes.
Okay, sir, here W is the equation, x plus 3y equals 1.
W is not the equation. W is a set x comma y where we have a relation between x and y by this straight line. Basically, W is the set of point on this straight line. So now is 0, 0 is on the straight line? No, right? Because this does not pass through origin. If we put x equal to 0 and y equal to 0, what I am getting? 0 equal to 1. This is absurd, right? Clear?
Yes, sir.
Yes, sir.
Anyone have any doubt in this?
No.
No, sir.
Okay.
So it is not
So
a
zero element
subspace.
is, huh?
Obviously, it is not a subspace.
So once I am getting this is not zero element does not exist, so I can say this is not a subspace. So W is not a subspace of R2, it is correct option. The last one. What about the middle two? Let's check.
Wrong
If V1
answer.
and V2 are inside W, is
option 2 is
inside
also
W?
right.
Huh?
It's also true, sir. Option 2.
Option 2 is correct.
Option 2 is correct.
Why?
No, I think
Because it will
incorrect.
because
X
it will
plus
always
3y
be a
is equal to
multiple
1.
of x plus 3y.
If you take
Someone is saying it is incorrect. Can you give me an example?
Sir, for example, if V1 we take 4 comma minus 1 and V2 we take minus 2 comma 1, then
So
if
first of all,
we
see, yeah, okay, I get it. Let me tell others. So first of all, check that these two are inside W. Is it true? All of you can check it.
yes, it is true.
These 2 points are on the line, right?
Yeah.
Okay, then tell. Who was telling? I forget the name again.
then sir it's when
Priyanka.
V1 plus V2 it will come 2 comma 0.
2 comma 0, right?
0.
So now is this point 2 comma 0? Is it inside W?
No.
No, right?
No.
So this is not true. Is it clear to everyone?
So
It is true, sir.
It is
V1
true,
plus
na?
V2
It is
not belongs to W.
not belongs to W. So
Not belongs to W. Then sorry.
this option is true actually.
This option is true. Option is true. Right.
Because if even in broader sense, if we add x plus 3y is equal to 1 twice,
you
it will
can
always
do it in
become
general. Right.
It will always come in multiple of it.
Exactly. Right.
And it will cancel
Right.
away.
And what about the next one?
Option 3 is correct.
Same thing.
It is saying inside W.
And then wrong answer.
Incorrect.
Incorrect answer. Can you give me an example?
So if we multiply
Minus
the
1 simply.
4 comma minus 1 by 2, then it will come 8 minus 6, which will be 2.
Correct. Everybody understood that?
Sir, and fourth option, sir. Fourth option.
No, it is not a subspace because 0 element does not exist. Means at least one of these failed means it is not a subspace, right?
Sir, option C, can you please explain?
So it is also.
Option.
Yeah. Which one?
Explain the option. Option 3.
Option, which option?
3. Option.
Option 3. So if you take suppose 4 comma minus 1. So 4 comma minus 1 is inside W, right?
No, sir, I did not understand C belongs to where you said C.
I will come into C. So I will come into C. First of all, see this V belongs to W. So I am taking this my V. This 4 comma minus 1 is inside W, right?
Yes, that's true. Yes.
Right. Now take any C in R. So I can take C as minus 1. I can take that.
Okay.
I can take that.
Yes, sir.
Okay. So what is C into V? This is my V. What is CV?
Minus 4, 1.
Minus 4, 1, right?
Yes.
Correct? Now
Yes.
is minus 4 comma 1 satisfy this property?
Minus 1 it yields, not 1.
plus 3,
Right?
it becomes minus. It becomes minus.
So x plus 3y means what? Minus 4 plus 3. That means minus 1. So this is not satisfying, right?
Yes.
So C comma C into B does not belong to W. So this option is incorrect. Is it clear?
Yes.
Yes, sir. Thank you.
Okay.
Hello, sir.
Yeah.
Sir.
Yeah.
Sir, 0, is 0 vector here. Regarding usual
Yeah,
addition,
right.
sir.
Right.
Usual addition.
That's why I have told while I have given the problem, this is with respect to usual addition. This should be mentioned in the question, but yeah, it should be in the question, right? Okay. Any doubt till this point? Any doubt till this point?
No, sir.
All right.
So,
Okay.
sir, are we supposed to always go by hit and trial, or there is some sure shot method or generalized way of solving?
Where are you going hit and trial method?
Like we have assumed 4 minus 1 and minus 2 1.
That is clear. No, if this does not, I mean, this is a straight line. If you add 2 points on a straight line, it is obviously you should have an intuition that the point should not lie in the straight line, right?
Yes, sir.
That is your obvious gut feeling should say. Then you have to try to find the example to prove.
Okay, yes, sir.
Okay, so first of all, your intuition should say that it should not be like that. Then you find the example.
Yes, sir.
Okay, if your intuition says it should be true, you try to prove it.
Okay. We
And
should follow our
means you have a
intuitions.
concrete proof.
Okay.
Right? You should have concrete proof. Okay. So I think we can stop at this point.
Can I ask something else beyond this?
Thank you, sir.
May stay back a little bit longer. I have a couple of questions from activities. I would like to understand what I am doing wrong.
You can feel this one also. Yeah, go ahead.
Yes, sir.
Activity question you want to ask me regarding activity questions?
Yes.
What's your doubt here? I mean, I will not solve any activity question. That's first I will tell you.
That's okay. I just want to. It is not. It is 3.4 actually.
Okay. What is there?
3.4. Let V be a vector space and non-zero vectors V1, V2, V3, and V4 belong to V. If V is a linear combination of Vi, V1 is a linear combination of Vi, where I is 2, 3, 4, then which of the following is correct? Okay.
So you are stuck at some option where V4 is taken on the other side, but it is still not saying, right? Something like that.
Yeah, basically V1 is a linear combination
of... So have you considered the case where one of the scalar can be 0 also? That is my hint for you.
Okay.
One of the scalar can be also be 0, right?
Scalar can be...
Scalar can be 0. That is real number. Can be 0.
Okay. I mean, like 0, 0 vector is what?
Now can you check that? That is the answer basically, I would say.
One more thing.
You think.
Sir, generally...
When you are taking all the vectors on the other side and one on the other side, okay, now you have to make it 1. The coefficient you have to make it 1. So basically you have to divide with the coefficient, right? Can you get what I am saying?
I don't think, because I am looking at a specific option, because V1 is a combination of 2, 3, and 4.
Right.
Okay, and one of the options is V1 must be linearly independent. I'm stuck at this place. Why is it independent when it is dependent on the other 3?
Okay. So first of all, tell me what do you understand about linear independence? What does that mean?
Linear independence means if the coefficients that are there for 2, 3, and 4, vectors 2, 3, and 4 are, if it is only when there is 0, then it means it is linearly independent. no other coefficients are actually
if we write all the things as, what should I say? I mean, sum of those should be 0, then all the coefficient must be 0, right?
Yes. If
Then?
that is the only condition in which they are I mean, we're talking about them as independent. The other way of interpretation is if one is scale of the other.
1 minute, I am opening it. Can you see it?
Yeah.
So this is of the earlier term, maybe not this term. But okay. Week 3, right?
Week 3, 3.4 activity.
3.4. Which one?
Question 4.
Question 4, this one, right?
Yes, the fourth option is what is confusing me. Not confusing me. I'm not able.
Fourth option, this V1 must be linearly independent.
Yeah.
Any singleton set is always linearly independent.
But V1 is a combination of 2, 3, and 4. So
that doesn't matter. That's why I asked you what linear independent mean.
Because alpha into V1 is equal to 0. That's why alpha should be 0 for linear independent.
So I am writing.
Suppose sir,
we
take
A
into V1
is equal to 0. 1 minute. Let me write. So what does linear independence mean? Suppose I have some vector V1, V2, V3 to Vn.
Okay.
If I am writing as a linear combination like this, then the only solution for alpha 1, alpha 2, alpha n is 0. There is no other solution, right? That is linear independent.
Correct.
Right?
Yes.
Now I have a only set V1. Okay. This is my single
V1 is non-zero.
V1 is non-zero, right?
Okay.
Now the linear combination, if I have to write it in a linear combination to make it 0, that means alpha V should be 0, right?
0.
What this alpha can be? Other than 0. Can there be any other alpha which is non-zero?
No, sir. No.
So this alpha must be 0, right?
Yeah.
That was the definition of linear independence.
Yeah.
Right?
Yep. Sounds silly when you explain it
any
like that.
Any singleton set is linearly independent.
Yeah.
Any singleton non-zero set.
Yeah. Sorry about that because
it is zero vector, then it is not.
Yeah. But
because for zero vector, what you will do?
Yeah.
For zero vector, what you will do to make it 0?
0.
What should be the alpha?
That can be
alpha
anything.
Should be non-zero.
0.
Any non-zero real number you can take, right?
Real number, yeah.
It can be anything.
Then you can take 1 because 1 into V is V,
Yeah.
Axiom. So you can take 1. 1 into 0 is 0. So there is a non-zero alpha. Yeah.
Yeah.
So in the same question, option number 3.
That's why I did not want to open the activity question. Yeah, what in option number 3?
The same question, option number 3 must be linearly independent. V2, V3, V4. Since V1 is not equal to 0, then this also should satisfy, because in the question it is given V1 is equals to some constant.
The question is given that V1 is a linear combination of V2, V3, V4.
So it means V1 is equals to alpha 1 plus V2, alpha 2 plus V3.
Right.
In such fashion, I can write it. And we have said V1 is not equal to 0. Then this set should also be linear V2, V3, V4.
Why?
Because V1 is not equal to 0. No?
So
if it is not equal to 0.
What you have to show? If you have to show that this is linearly independent.
Yeah.
What you have to show? You have to show if this is a solution, this suppose alpha V2, beta V3, gamma V4. If this is 0, if you have to show alpha, beta and gamma are 0. Can you show that? Can you show that?
This is equal to V1, you have written it is equal to 0.
No, if you want to show that V2, V3, V4 are linearly independent, what you have to show? You have to show this alpha, beta, gamma should be 0.
Is equals to 0. Yes, correct.
Can you show that? What you have given? You have given that V1 is a linear combination of some other alpha beta, say A, B, C, A, V2, B, V3, C, V4. This is given. Now from there, can you show this? If you cannot show this, give a counter example that will prove your answer. If you cannot show it, try to produce a counter example that this is not the case. These are not linearly independent. Okay.
Okay, so it means we have to assume we cannot prove it, so it is linearly.
I mean, if you cannot prove it, then try to give a counter example. That is my point. Okay. Anyway, I will discuss it again in Thursday. That's why I am not going in details.
Hello, sir.
Okay.
Yeah.
Sir.
Yeah.
Sir, I have just one question, sir. Suppose we want to write a system of linear equation Ax is equal to B, and the X is given like a subset of vector space. Then what should we take for X here? X transpose or only X, sir?
So basically, you are saying you are writing Ax equal to B.
Yeah.
Okay. So X is from some Rn. X belongs to some
Yeah,
Rn.
yeah,
That's what you are saying, right? So in Rn, basically we generally represent it by row. Okay, like this, Xn. Okay. But when I am writing this representation, I am taking like this. So
Column.
it's transpose column.
Okay. So we should take X transpose here with respect to X belongs to Rn.
Exactly. Okay.
Hello.
Yeah.
Yes.
हेलो
Yeah, Priyanka.
सर ये वीडियो 1 में जो सर ने नॉन एग्जाम्पल्स पढ़ा बताए थे वो सर समझ नहीं आया इफ यू कैन टेल मी वन थिंग
कौन सा
सर वीडियो 1 में नॉन एग्जाम्पल्स बताए
क्या
थे सर ने
एग्जांपल क्या था थोड़ा बोल सकते हो
it was let us define addition and scalar multiplication in R2 as follows x1 x2 plus y1 y2 is equal to x1 plus y1 x2 minus y2 ये माइनस कैसे आया मुझे ये समझ में नहीं आया
नहीं डिफाइन किया इसने जैसे हम लोग ने आज डिफाइन किया था ना
ओके
तो एक डिफाइन किया तो उस डेफिनेशन से वो वेक्टर स्पेस नहीं बन रहा है जैसे हम लोग ने ये वाला डिफाइन किया
या आई गॉट इट
लाइक हम लोग ने स्ट्रक्चर बनाया था
हाँ वो एक अलग स्ट्रक्चर है
Okay, I will then again revisit that question. One more question. वैसे ही video 2 में he was proving. I understood that it is given. I will again revisit that question.
Yeah. Okay.
In video 2 also, he was describing the corollaries of cancellation law of vector addition, in which he proved that v prime is equal to v double prime. I didn't understand what is v double prime. What was he trying to say? The vector v prime described in 4 is unique and it is standard to refer to it as minus v. Then he supported it with that v prime is equal to v double prime.
So basically he was trying to show that inverse is unique. Whenever inverse exists, it is unique. So suppose v prime, I am taking v prime as my inverse. Okay. So I want to show that this is unique. So suppose it is not unique. So there exists another element, another vectors, which I am calling it v double prime. Okay, I can call it. Now, if I can show that v prime is equal to v double prime, then I am done. Is it okay?
Okay, got it.
यूनिक दिखाने के लिए क्या दिखाना होगा? मतलब एक दूसरा कोई एग्जिस्ट करता है, ये हम लोग एज्यूम कर लेंगे, उसके बाद दिखाएंगे कि वो दोनों बेसिकली सेम ही है.
Okay.
तो हमने जो एज्यूम किया था वो गलत है.
Okay, understood. Sir, एक और है, sorry. The plane of the two vectors are 0 to 1 and 2 to 0 can be expressed by the equation 2x minus 2y plus 4z is equal to 0. ये कैसे निकला?
अच्छा, एक और एक क्या है यहाँ पे?
2 to 0.
So plane passing through these 2 points, right?
Yeah. Equation कैसे बने इसके?
minus
ये
equal to
थोड़ा
x to
मतलब
minus
अभी
2 into
निकालना
x.
थोड़ा मुश्किल है. So basically any plane which is, and this is passing through origin also, right? Any plane passing through origin.
He just expressed that plane of the two vectors. These two vectors can be expressed by the equation this, which is 2x minus 2y plus 4z is equal to 0.
2x plus 2y minus 4z equal to 0. Right?
2x minus 2y plus 4z is equal to 0. Minus, yeah, this one is plus, z1 is plus.
Okay.
Yeah.
And
How
anyone
we
is saying
conclude
something?
this?
Yeah, someone is asking something.
Yeah. No, the same question I asked in the forum. Someone said we have to make it as a XYZ plane and then start plotting it. Then I even asked.
Simply put in the formula.
This I mean, this require the definition of span. Okay. You know what span is? Span of a set.
No, sir.
So
Or
suppose,
we can also use the concept of vector 3D in +2 taught in +2, na sir.
but I don't want to go there.
I did my +2 30 years back. Sorry.
So I will
me
not go
15,
there.
20 years back.
Okay. So suppose I have two vectors in this set. Okay.
Okay.
There can be more than two vectors also. Okay. Span means set of all linear combination. Okay.
Yes, sir. Yes.
So basically, alpha 1 v1 plus alpha 2 v2, where alpha 1 and alpha 2 are coming from real number. Okay. So basically, all the linear combination of these vectors, these two vectors. Okay. This is called linear combination. Set of all linear combination is basically our span S. And this span S is basically a vector space that I can show. I am not going to the details because again I have to do that. So this is a vector space basically. So this vector space, if we consider this is my set S with these two vectors, the span of this S will be this plane. Because if you write this, what you will get? 0, 2. So suppose instead, okay, A and this is B, 2, 2, 0. What I am getting? 0, 2A. This you can say no with respect to usual addition. 2B, 0. So what will be that? 2B, 2A plus 2B and A. Correct? Till this we have understood?
Yes, sir. Yes, sir.
Okay. Okay, great. Now what I should do, this is my X, this is my Y, this is my Z. Okay, as a coordinate. Right? Is there any relation between X, Y, Z? Is there any relation? So what is X? X is 2B, Y is 2A plus 2B, and Z is 2A. Correct?
That is A.
A, sorry. A. Now, is there any relation? Can you say? So I can write 2Z equal to 2A, right? From this one.
Yes, sir.
And I will replace this Y equal to, so 2A
Z.
instead of 2A, I am saying
2Z.
Z. And instead of 2B, I am saying X.
X.
Right? So what I am getting, X minus Y plus 2Z equal to 0. This is the relation.
Okay, understood.
This is the plane.
Yeah, it is just multiplied by 2.
Multiplied by 2.
But sir, I have a question. 4Z equal to A होना चाहिए ना? Z equal to A by 4. 4Z equal A.
क्या?
I mean, Z equal A लिखा हुआ है ना आपने, but 4Z equal A होना चाहिए ना? If we compare both the equation.
No, I am whatever I am getting here, I am writing the first one as X, second one as Y, and third one as Z.
I mean, you are assuming or you are equating?
Yeah, sir is assuming.
No, this is the natural way. No, this is the first coordinate, second coordinate, third coordinate. First one is X, second one is Y, third coordinate is Z. Right? I am not assuming anything. This is the way. I mean, if you want to express something in R3, the first coordinate is X coordinate, second is Y coordinate, third
Sir, वो
coordinate is Z
पूछना
coordinate.
चाह रहे हैं कि आप अपने मन से उसको X, Y, Z ले रहे हैं ना? That's what he wants.
नहीं, आपने मन से नहीं ले रहा. मतलब this is the
नहीं, एक थोड़ा सा ऊपर करना, because you write an equation. ये 2x minus
ये हमें दिखाना है basically.
Yes sir.
ये अभी नहीं है हमारे पास.
अच्छा, okay. I thought you are equating both the things. So
नहीं, ये भूल जाओ.
Okay, sorry.
हमारे पास ये vectors है, ये दो vector है.
We are given two vectors and we have to find
given two
equation.
vectors. I am calculating what is span of S. Basically, I want to express my span of S as a plane.
Okay.
That will be a plane. That will be a plane passing through origin. So I want to find the equation of that plane. How we will find that? This is the way I can find the equation. Okay. Is it clear now?
Yes, sir. Thank you so much. Sir, just one last question.
Yeah.
So what is trivial and non-trivial?
So that depends on the context again. In which context we are talking about. So basically trivial means, suppose I am talking about subspaces, right? Right now I was talking about that. So basically zero subspace and the whole plane, whole subspace are 2. Or any vector space, whole vector. That is basically trivial one. And all other are non-trivial.
Trivial is zero subspace. I mean,
and
zero.
Which is obvious that is trivial. Okay. So for R2, as I was talking about, for where it is, for R2, suppose V is my R2. These two, 0, 0 and R2. R2 is the whole subspace, 0, 0, the singleton point. This is also a subspace. Now these two are trivial subspaces because this is obvious. When I am talking about Rn, the origin, and whole Rn, these are two obvious subspaces. I mean, these two will always be subspace for any n. Correct. So these are trivial subspaces. Now, for non-trivial means what else are there, which is not obvious. Is it clear?
Okay, sir. Thank you so much.
Yeah. Okay.
Sir, one question can I ask?
Now. Next day.
Sir, if you are, yeah, sure. If you will.
No, what is your question? Let me.
Sir, on linearly dependency. Sir, any set of 4 vector or will be in R3 as linear dependent set, right?
Exactly, right.
Yeah, sir. So
any 4 vectors in R3 is linearly dependent.
Yeah, so I just want to know that why. I'm not able to visualize this. Yeah.
Okay. Okay. So I will not give you the exact proof now, but I will give you a visualization.
Yes, sir. Yes.
Say if you take in R2 any 3 vector in R2.
Yeah. Okay. Yes, sir.
Okay. So let us take that. Any 3 vector in R2, what I am getting. So suppose 3 vector. So this is my R2. X-axis and y-axis. So any point here is a point in R2. Okay, I am taking any 3 point here. So my claim is when I am taking 3 point here in R2, I can write the third one as a linear combination of first 2.
First 2, correct. X and Y.
Why?
Yeah.
Why?
Sir,
can you tell me why?
Sir, because it will pass through between these two.
Not really. Say, suppose my first point is, so I am giving you a trivial example, 1, 0. Second point is 0, 1.
0, 1. Yes, sir.
Now you take any other point in XY plane, any other point.
Yes, sir. Yes, sir.
4, 5 or anything. You can write this as a linear combination of these two, right?
These two, correct. Yeah.
How?
Yes, sir.
Like this.
Yes, sir. 4 into 1, 0 plus 5 into 0. Yeah.
Let's look like resultant vector.
Exactly this kind of resultant vector, but this is ultimately what you will see in week 4. This is basically the basis.
Basis, correct. Yeah.
This is of a vector space.
Yeah.
This one. So,
sir, basis is like by which we can write all the linear combinations.
Exactly. I mean, that is the minimal number of element.
Yes, sir.
By which you can.
By which we can find all the subspace.
Exactly.
Yeah.
And the number of elements in the basis is called the cardinality.
Cardinality.
So called the dimension. Dimension of the vector space.
Dimension of a vector space. Correct. Yeah.
Once I reach the dimension of a vector space by spanning it. Now, if you take any other vector in the space, you can express it, right? With respect to the basis. That's the point. R2, what is the dimension? It is 2. So once you take third vector, it can be expressed by the other 2.
Okay. Okay. So visualization part, I am not able to get it. Otherwise, it's fine.
Now is it clear?
Yeah, now it's little bit fine.
Yeah, I will explain it more later, but till now this is okay, right?
Yes, sir. Yes, sir. Okay. Yeah, very okay.
Okay, fine.
Thank you so much, sir. Very beautiful session once again.
Yeah.
As usual.
On Thursday, we'll have to join on the same
Thank you, sir.
link.
Thank you very much.
Sir, please आइएगा अगले सेशन में
will
भी.
be same, I think.
Link
will be same.
Okay.
सर अगले सेशन में भी हो सके तो प्लीज आइएगा. It will be very. सर अगर कुछ क्वेश्चन पूछना हो तो सर आपको मतलब मैसेज करके डिस्कोर्स पे पूछ सकते हैं.
हाँ डिस्कोर्स में मुझे टैग कर देना.
Thank you so much.
Thank you, sir.
Good night.
Yeah.
Thank you, sir. Thank you very much.
Thank you, sir. Good night.
Sir, and good night.
Good night.
Thank you very much for staying this much. Another 1 hour extra. And
in-depth session.
Thank you.
Thank you, sir. Thank you so much.
Thank you, sir. Good night.
Thank you. Good night.
Good night.
Bye, sir. Good night.